What if you could step outside of time itself, not just watching history unfold but walking through it, witnessing the birth of civilizations or the distant future of our universe? What if the secret to that impossible journey has been hiding in plain sight, woven into the fabric of the cosmos within the most enigmatic and powerful objects we know? We are about to embark on an exploration of 30 incredible theories that connect the deepest mysteries of black holes to the tantalizing possibility of time travel. This isn't just a lecture on complex physics, it's an adventure into the furthest reaches of human understanding, where the laws of the universe as we know them begin to bend and warp. Think about the sheer ambition of that quest. For centuries, time travel has been the domain of fantasy and science fiction, a dream that captures our collective imagination. Yet, what if the science fiction of our past is slowly becoming the scientific frontier of our present? The answers may not lie in building a complex machine in our garage, but in looking up at the heavens and confronting the ultimate cosmic paradoxes. Black holes are not just empty voids, they are the universe's most extreme laboratories, places where gravity is so intense that it twists the very fabric of spacetime into knots. At their edge, at the boundary known as the event horizon, time itself behaves in ways that defy our everyday experience. To even approach these ideas is to challenge everything we think we know about cause and effect, about the past and the future. This journey we're starting together will take us from the brilliant insights of Einstein to the cutting-edge speculations of modern theoretical physicists. We'll investigate wormholes, cosmic strings, and the bizarre concept of closed timelike curves. We'll ask if falling into a black hole could be a one-way trip to another era, or if these celestial giants could be used as natural gateways, bridges not just across space but across ages. The questions we confront are as profound as they are thrilling. Could an advanced civilization ever harness the power of a spinning black hole to open a passage through time? Is our entire universe potentially a holographic projection of information stored on a distant two-dimensional surface, an idea that could completely reshape our view of reality and time's arrow? Each theory we examine is a piece of a grander puzzle, a step closer to understanding our place in a cosmos that is far stranger and more wonderful than we ever imagined. So get ready to stretch your mind. We're going to dive into the heart of these cosmic mysteries together, unpacking concepts that are both elegantly simple and dizzyingly complex. This is an invitation to wonder, to set aside what you think is possible, and to join a voyage to the very limits of knowledge, where the line between science and profound mystery beautifully blurs. Let's begin. Our journey begins not at the edge of a black hole, but in the mind of one man over a century ago. Albert Einstein's theory of general relativity completely rewrote our understanding of gravity. Before Einstein, we thought of gravity as a simple, invisible force pulling objects together, much like Isaac Newton did when he saw an apple fall. Einstein proposed something far more radical and elegant. He suggested that gravity isn't a force at all in the traditional sense, but rather a consequence of the geometry of the universe itself. Think of spacetime as a vast, flexible trampoline mat. A massive object like our Sun sits in the center of that mat, creating a deep dip or a warp in the fabric. Now, if you roll a smaller marble representing a planet near that dip, it won't travel in a straight line. Instead, it naturally follows the curved path around the Sun, trapped in what we call an orbit. This brilliant idea that mass and energy tell spacetime how to curve, and that curved spacetime tells mass how to move, was the first key that unlocked the door to time travel as a serious scientific concept. It's within this warped geometry that something truly strange happens to time itself. This is the phenomenon of time dilation. The stronger the gravitational field, or the closer you are to a massive object, the slower time ticks for you relative to someone in a weaker gravitational field. It sounds like pure science fiction, but we have direct, measurable proof. Consider the astronauts living and working on the International Space Station. They are orbiting about 250 miles above the Earth, which means they are a little farther from the planet's mass than we are on the surface. As a result, their clocks actually run slightly faster. It's an incredibly tiny difference. They gain a few milliseconds over a 6-month mission, but our most precise atomic clocks can detect it. This effect is even more pronounced here on Earth. A clock placed at sea level, where gravity is slightly stronger, will tick a tiny bit slower than an identical clock on top of a mountain. Now take this concept and push it to its absolute extreme. What is the most gravitationally intense environment we can conceive of? The answer is a black hole, an object so incredibly dense that its gravity prevents even light from escaping. A black hole is general relativity's ultimate masterpiece, a place where spacetime is curved into an infinitely deep well. As you approach the boundary of this well, the event horizon, the warping of time becomes unimaginably severe. To a distant observer watching you fall in, your time would appear to slow down more and more, stretching seconds into years, centuries, or even millennia. You would seem to freeze in place, fading to red and then vanishing from view, as the flow of your time grinds to a near halt from their perspective. For you, of course, time would pass normally, but the universe outside would flash forward in a dizzying blur. This is not a theory about building a machine. It's a fundamental property of our universe, written into the fabric of reality by gravity itself. Einstein's work gave us the first real, mathematical glimpse into how the flow of time is not a universal constant, but a personal, flexible experience, shaped entirely by where you are and how you are moving. This profound insight that time is malleable is the indispensable bedrock upon which every single modern theory of time travel is built. But if simply approaching a black hole can warp time to such an extreme degree, what if we could find a way to travel through the distortion rather than just falling into the abyss? This brings us to our second theory, and one of the most enduring and captivating ideas in all of theoretical physics, the wormhole. Imagine the vastness of our universe. To travel from our galaxy to the next, even at the speed of light, would take millions of years. Now, picture a piece of paper with 2 dots drawn on opposite ends. The normal distance across the paper is immense, but if you could fold the paper, bringing those 2 dots to touch, you could create a tunnel or a bridge connecting them instantly. That is the fundamental principle of a wormhole, a theoretical shortcut or a tunnel through the very fabric of spacetime itself. It would be a cosmic subway system, connecting not just different locations, but potentially different moments in time. The roots of this incredible idea, just like time dilation, are found in Einstein's equations. In 1935, Albert Einstein and his colleague Nathan Rosen realized that the mathematical description of a black hole, a point of infinite density known as a singularity, could potentially be extended to form a bridge to another point in spacetime. This structure became known as an Einstein-Rosen bridge. In this view, what we perceive as the crushing singularity at the heart of a black hole might not be a final destination, but a throat or a passageway. One black hole could be connected to another, or perhaps even to a theoretical opposite called a white hole, which would spew out matter and energy rather than trapping it. This suggests a breathtaking possibility that black holes themselves could be the natural entrances to these cosmic tunnels. You wouldn't just be destroyed upon crossing the event horizon. You might be transported to another place or even another time, emerging from a linked white hole in a different part of the cosmos. It's a concept that feels lifted directly from the pages of the most ambitious science fiction. However, there is a monumental catch, a reason why we haven't found any of these shortcuts yet. The problem is one of stability. According to our current understanding, an Einstein-Rosen bridge would be catastrophically unstable. the moment it formed, the immense gravitational forces would likely snap the tunnel shut faster than the speed of light, crushing anything inside before it could complete the journey. It would be like trying to walk through a corridor that collapses behind you the instant you take your first step. This is where the theory ventures into truly speculative and fascinating territory. To keep a wormhole open and traversable, you would need something extraordinary to prop it open, something that could counteract the intense gravitational pull trying to crush it. Physicists propose that this would require what is known as exotic matter. Now, this isn't just matter that is rare or from another planet. Exotic matter, in this specific context, would have to possess a negative energy density, or in simpler terms, it would have to exhibit negative gravity. Instead of pulling things together like normal matter, this exotic substance would push spacetime apart, acting as a kind of cosmic support beam to keep the wormhole's throat wide open. While this sounds completely fantastical, faint echoes of such behavior have been observed in certain quantum effects, like the Casimir effect, where closely spaced metal plates in a vacuum experience a slight force pushing them together, which can be interpreted as negative energy in the space between them. We are not talking about mining truckloads of this material, however. The amounts generated in lab experiments are vanishingly small, while holding open a wormhole for a human traveler might require the negative energy equivalent of a star or even a galaxy. So, while wormholes are mathematically possible within the framework of general relativity, the practical barriers are, for now, insurmountable. They remain one of the most elegant and inspiring ideas in physics, a testament to the fact that the universe's rulebook might allow for incredible journeys, even if the instructions for building the ticket are written in a language we are only just beginning to understand. While the idea of wormholes presents a spectacular cosmic shortcut, it requires materials that may be pure fantasy. But what if the universe provides a ready-made time machine, no exotic matter required? This brings us to our third theory, which takes us from the static heart of a simple black hole to the dynamic, whirling chaos of a rotating one. Most people picture a black hole as a perfectly symmetrical, dark sphere, a static pit in space. Yet, reality is far more interesting. Stars rotate, and when they collapse into black holes, that spin doesn't just vanish. It becomes a defining feature, creating an object of immense complexity and power. In 1963, a New Zealand mathematician named Roy Kerr found a solution to Einstein's field equations that described precisely this, a spinning black hole. His work revealed a structure that is dramatically different from its non-spinning cousin. A Kerr black hole is not a simple point singularity. Instead, its immense rotation flattens it at the poles and bulges it at the equator, and the singularity at its center isn't a point but is stretched into a mesmerizing ring. This ring singularity isn't just a curious shape, it's a gateway to a realm of profound possibilities. The intense rotation of the black hole doesn't just warp space, it drags it along, a phenomenon known as frame dragging. Imagine stirring a cup of tea with a spoon. The liquid closest to the spoon is pulled around most strongly. A Kerr black hole does this to the fabric of spacetime itself. This creates a region around the event horizon called the ergosphere, a whirling, oblong shell of distorted spacetime where nothing can remain stationary. Everything, including light itself, is forced to move in the direction of the spin. It's within this maelstrom of twisted geometry that something truly mind-bending emerges, the potential for closed timelike curves. To understand this, we need to break down the term. In relativity, a timelike path is one that a material object traveling below the speed of light can follow through the four dimensions of spacetime. A curve is just the path itself. In our normal, everyday universe, these paths always move forward in time. You are always at a later moment than you were a second ago. But within the specific, warped geometry inside the ring singularity of a Kerr black hole, The mathematics suggests these timelike paths could curve so severely that they loop back on themselves, connecting to a point in their own past. A closed timelike curve is exactly that, a path through the universe that, if you were to follow it, would bring you back to the very event where you started your journey. You could, in theory, meet your younger self before you ever left. This isn't just moving fast to see the future. This is a potential mechanism for traveling into the past. The key to this bizarre possibility lies in that ring singularity. Because it's a ring, not a point, it might be possible to pass through its center without being destroyed by infinite density. The mathematics suggests that this passage could lead you into a region of spacetime where the usual rules of cause and effect break down entirely, a place where these time loops are not just possible but unavoidable. It presents a scenario where you could witness historical events or potentially even interact with them. However, before we start planning our trips to ancient Rome, we must confront the monumental hurdles. First, actually reaching the region where these closed timelike curves exist would mean surviving a journey through the inner event horizon, a boundary where, according to some calculations, tidal forces might become infinite, ripping any object apart in a phenomenon known as the inner horizon instability. Second, and perhaps more fundamentally, is the problem of paradoxes. The classic example is the grandfather paradox. If you travel back in time and prevent your grandfather from meeting your grandmother, how could you ever have been born to travel back in time in the first place? The existence of closed timelike curves seems to violate a fundamental principle of logic and causality that our universe appears to rely upon. Physicists have proposed several potential resolutions. One is the Novikov self-consistency principle, which suggests that the laws of physics simply will not allow you to create a paradox. Your actions on a closed timelike curve would be predetermined, woven into the timeline in such a way that you could never actually change the past, only fulfill it. Another, even more speculative idea comes from the many worlds interpretation of quantum mechanics, which posits that any action you take in the past would simply branch off a new, parallel universe, leaving your original timeline untouched. While the existence of closed timelike curves within Kerr black holes remains a highly controversial and purely theoretical speculation, their power as a concept is undeniable. They force us to confront the deepest questions about the nature of time, causality, and the very structure of reality, showing us that a spinning black hole is not just a cosmic vacuum cleaner, but a knot in time itself. The mind-bending possibilities offered by a spinning black hole's interior seem to suggest the universe might allow for journeys through time. But what if the cosmos has its own fail-safe mechanism? A set of cosmic rules designed to prevent such reality-shattering paradoxes from ever occurring. This leads us to a profound and influential idea known as the cosmic censorship hypothesis, proposed by the renowned physicist Roger Penrose. Penrose was deeply troubled by the implications of the naked singularities that the mathematics of objects like Kerr black holes seem to permit. A singularity, as we've discussed, is a point of infinite density where the known laws of physics, including general relativity, simply break down. In a standard black hole, this problematic point is hidden from the rest of the universe behind the one-way curtain of the event horizon. Nothing that happens inside can affect the outside, effectively containing the breakdown of physics. But what if a singularity could exist without this protective shield? A naked singularity would be an exposed point of infinite density, visible to and able to influence the entire universe. The consequences of such an object are staggering. From a naked singularity, the unpredictable and lawless physics at its heart could leak out, sending signals of pure causality violation across the cosmos. Closed time-like curves wouldn't be confined to some inaccessible inner region. They could spill out into the wider universe, making time travel and its attendant paradoxes not just a theoretical curiosity for brave explorers, but a potential feature of everyday reality. The grandfather paradox wouldn't be a thought experiment. It could become a tangible, universe-breaking problem. Penrose's cosmic censorship hypothesis is in essence a bold conjecture that the universe finds such a possibility so abhorrent that it actively prevents it from happening. He proposed that nature itself possesses a form of cosmic censorship, ensuring that every singularity that forms from realistic, natural conditions is always safely hidden behind an event horizon. It's as if the universe has a built-in referee whose primary job is to maintain the fundamental rule of cause and effect, declaring that singularities, by their very nature, must never be put on public display. This hypothesis isn't a proven law of physics, but rather a deeply held belief among many physicists about how the universe should behave to remain logically consistent. If true, it would act as the ultimate guardian of chronological order, placing the wild, paradox-ridden world of time travel firmly off-limits. It suggests that the gateway to the past offered by a Kerr black hole's ring singularity is permanently locked, its key thrown away by the fundamental laws of nature. We are free to imagine what lies beyond that gateway, but we may be forever barred from ever stepping through. This idea forces us to consider a fascinating philosophical question. Are the laws of physics we are discovering merely descriptive, or are they also protective? Is the consistency of our timeline not just a happy accident, but a fundamental feature that the cosmos actively enforces? The cosmic censorship hypothesis leans toward the latter, painting a picture of a universe that, for all its strangeness, has a vested interest in maintaining a stable, paradox-free reality where the past stays in the past. But if the universe truly does censor its most dangerous secrets, locking away singularities to protect causality, then we are left with a profoundly stable, if somewhat predictable, cosmos. However, the next theory on our journey completely shatters that stability, turning our understanding of black holes on its head and introducing one of the most baffling puzzles in modern physics. This is the story of Hawking radiation and the terrifying information paradox, ideas born from the brilliant mind of Stephen Hawking. Up until the early 1970s, the textbook description of a black hole was simple: things fall in and nothing, not even light, ever comes out. They were considered the ultimate endpoints of gravitational collapse, eternal and unchanging. But Hawking realized this picture was incomplete because it ignored a crucial player, the quantum world. He asked a deceptively simple question: what happens near the event horizon when we consider the strange, probabilistic rules of quantum mechanics? In the quantum realm, empty space is not truly empty. It is a seething, bubbling foam of virtual particles. These are particle-antiparticle pairs that spontaneously pop into existence from the vacuum, borrowing energy from the universe for an incredibly brief moment before they collide and annihilate each other, paying back the energy loan. This constant, frantic activity is happening everywhere, all the time. Now, place this quantum frenzy at the very edge of a black hole's event horizon. Hawking theorized that if such a particle pair appears right at that boundary, a monumental theft could occur. One particle with negative energy could fall across the event horizon while its partner with positive energy is ejected outward into space. From the perspective of the universe, this looks just like radiation emanating from the black hole itself. The black hole has, in effect, paid the energy loan for the escaping particle by absorbing the negative energy one. And here is the truly revolutionary part. By absorbing that negative energy, the black hole loses a tiny, tiny amount of its own mass. This is Hawking radiation. It means that black holes are not permanent fixtures of the cosmos. They slowly, over incomprehensible stretches of time, evaporate. A solitary black hole of stellar mass would take many times the current age of the universe to evaporate significantly, but the principle is established. Black holes are not black, they glow with a faint thermal heat, and in doing so, they are slowly fading away. This stunning discovery bridged the worlds of general relativity and quantum mechanics for the first time, but it also created a crisis. The radiation Hawking predicted is purely thermal. It contains no specific information about the particular things that fell into the black hole. It doesn't matter if the black hole was formed from a collapsed star, an old spaceship, or a library of encyclopedias. The Hawking radiation coming out would be exactly the same, a generic heat signature. This leads us directly to the heart of the information paradox. In quantum mechanics, information is never truly lost. The universe is fundamentally deterministic in its probabilities. If you know the complete quantum state of a system at one time, you should, in principle, be able to calculate its state at any other time, past or future. The information about what fell into the black hole, the specific arrangement of atoms that made up the star, the spaceship, or the library, must be preserved somehow. But according to Hawking's original calculation, when the black hole finally evaporates completely, all that is left is this formless, featureless radiation. The specific, detailed information about everything that ever fell in has been irretrievably erased from the universe. This is not just a loss of data, it's a violation of a core pillar of quantum theory. It's as if you burned a unique, handwritten book and all that remained was the generic heat from the fire, with no trace of the words, the sentences, or the story ever being recoverable. For decades, this paradox pitted two of our most successful physical theories, general relativity and quantum mechanics, against each other in a fundamental and seemingly irreconcilable conflict. So, how could this cosmic contradiction be resolved, and what could it possibly tell us about time? One of the most promising and mind-bending solutions comes from the holographic principle. This idea suggests that all the information that falls into a black hole is not destroyed, nor is it lost inside the singularity. Instead, it is encoded pixel by pixel on the two-dimensional surface of the event horizon itself. Think of it like a cosmic hard drive. When a three-dimensional object falls into a black hole, its information is not compressed into the tiny singularity. It is smeared and stored as incredibly complex, microscopic ripples and patterns on the event horizon surface. Then, as the black hole emits Hawking radiation, this process is not random. The escaping particles are subtly influenced by this encoded information, like a radio broadcast being modulated by a signal. The radiation, therefore, is not purely thermal after all. It carries the scrambled, hidden history of everything the black hole has ever consumed. The information is not lost, it is transformed and eventually released back into the universe as the black hole evaporates. Now connect this to the nature of time. The arrow of time, the reason we remember the past and not the future, is deeply linked to the increase of disorder or entropy in the universe. The holographic storage of information on the event horizon is a direct measure of a black hole's entropy. This means the process of information falling in, being encoded, and slowly being radiated back out is a profoundly thermodynamic process, intimately tied to time's relentless forward march. But could this scrambled information emerge in a different time period? If the information is faithfully preserved and released, it re-enters the causal flow of the universe at the moment it is radiated, which is billions of years after it fell in. In a very real sense, the black hole acts as a time capsule, not of objects but of quantum information. It takes the data from the past and releases it into the far future. This doesn't allow for controllable time travel, but it does create a bizarre kind of temporal displacement. The story of your existence, the information that makes you you, if it fell into a black hole, would not be destroyed. It would be frozen at the horizon, slowly imprinted onto the radiation that will one day warm a distant future cosmos, telling its story to a universe that has long since forgotten the era from which it came. If the holographic principle paints black holes as cosmic archivists, faithfully preserving information across eons, it still leaves us with a monumental question about the nature of causality itself. What happens to the flow of cause and effect if we ever manage to navigate the closed time-like curves that might hide within a spinning black hole? Would the universe simply unravel? This profound dilemma brings us to a theory that offers a radical and elegant solution, one that attempts to restore order to the chaos of potential paradoxes. It's called the Novikov self-consistency principle, proposed by the Russian astrophysicist Igor Novikov. At its heart, this principle makes a simple yet astonishing claim. If time travel to the past is possible, then the universe is fundamentally constrained in such a way that you can never, under any circumstances, change the past. Your actions as a time traveler were always a part of the history you are visiting. There is no alternate timeline, no rewriting of events. The past you travel to is already the past that included your arrival and everything you did there. Think of the classic grandfather paradox not as a problem to be solved, but as an impossibility that the laws of physics proactively prevent. According to Novikov, you could certainly travel back in time with the intention of preventing your grandfather from meeting your grandmother. You could find him, you could raise the weapon, you could pull the trigger, but the principle asserts that something would always interfere. The gun would jam. A sudden noise would startle you, a passerby would bump your arm, your own conscience might stop you at the last second. The sequence of events would play out with a kind of cosmic inevitability, ensuring that your grandfather's life, and thus your own birth, proceeds exactly as it always did. Your presence in the past was not an intrusion, it was a feature of that timeline from the very beginning. Your attempt to change history becomes the very reason history unfolded the way it did. Perhaps your appearance in the past and your failed attempt is what motivated your grandfather to join a certain club where he would eventually meet your grandmother. Your actions, even your paradoxical intentions, become woven into the immutable tapestry of the past. Now, apply this self-consistency principle to the environment of a black hole. Imagine you discover a stable, traversable wormhole or navigate the ring singularity of a Kerr black hole, finding yourself on a closed time-like curve that takes you 24 hours into the past. You emerge and decide to conduct an experiment. You write a specific number on a piece of paper, let's say the number 7, seal it in a box and give it to a friend for safekeeping. You then travel back in time one day. You meet your friend from yesterday and ask them to open the box. What number is on the paper? The Novikov principle dictates that the only logically consistent outcome is that the number must be 7. It cannot be any other number. Why? Because the piece of paper you are looking at in the past is the very same piece of paper you will write on and seal in the future. The information, the number 7, exists in a closed loop. There is no origin for that number, it simply exists consistent through time. Any attempt to write a different number in the future would create a contradiction that the universe forbids. The implications of this are staggering. It suggests a universe that operates not with a single, linear timeline, but with a single, self-consistent and potentially knotted timeline. Free will in this context becomes a profound philosophical puzzle. Do you truly have a choice, or does the self-consistency of the universe mean that all your actions are predetermined to fit a pre-existing pattern? Novikov argued that you still have free will, but you are only free to choose actions that are consistent with the established past. You would find yourself wanting to make the choices that align with the timeline, your desires themselves shaped by the necessity of consistency. It's a concept that feels almost like fate, but framed in the language of physics. For black holes specifically, this principle provides a potential answer to why the cosmos doesn't tear itself apart from paradoxes, even if closed time-like curves exist. The violent instabilities and infinite energies that some models predict at the inner horizons might be the universe's brutal mechanism for enforcing this consistency, physically preventing any action that could lead to a contradiction. The Novikov self-consistency principle transforms the black hole from a potential paradox generator into a guardian of chronological order, a natural mechanism that allows for the bending of time while fiercely protecting the unchangeable nature of history. While the Novikov principle offers a compelling way to resolve the paradoxes of time travel, it operates within a universe that still follows the familiar forward march of time. But what if we could reverse that flow entirely, turning the ultimate cosmic sink into a fountain? This leads us to one of the most exotic and speculative concepts in all of theoretical physics, the white hole. If a black hole is a region of spacetime from which nothing can escape, a white hole is its exact theoretical opposite, a region of spacetime into which nothing can enter. It is a point of pure, relentless emission, constantly spewing out matter and energy into the universe while eternally refusing to accept anything in return. Think of a black hole as a one-way street leading into an impenetrable vault. A white hole, then, would be that same vault, but with the doors welded open, its contents exploding outward in a continuous, unstoppable eruption. The mathematics of general relativity is beautifully symmetric, and the equations that allow for black holes also permit these white hole solutions. They are the other side of the cosmic coin, emerging as a natural counterpart when you follow the math to its logical conclusion. One fascinating interpretation, championed by the physicist Igor Novikov himself, is that a white hole is simply a black hole seen from a different perspective in time. From our forward-flowing temporal viewpoint, a black hole is an object that consumes. But if you were to reverse the direction of time in the equations, the black hole's event horizon would become an impassable barrier from the outside, and its interior would become a source of infinite energy, behaving exactly like a white hole. This suggests that what we perceive as a black hole in our universe could, from a reversed time perspective, be a white hole in another universe or another epoch. This idea becomes even more captivating when we consider the potential connection between white holes and the origin of everything, the Big Bang. The standard model of cosmology describes the Big Bang as a singularity, a point of infinite density from which all matter, energy, space, and time erupted. Sound familiar? The description is remarkably similar to a white hole. Some theorists have proposed that our entire universe could, in fact, be the interior of a colossal white hole. The initial explosion wasn't just an event in space-time. It was the moment the white hole's event horizon formed, and we have been living in the cascading outflow of its radiation and matter ever since. In this view, the Big Bang was not a unique, unrepeatable event, but rather one instance of a natural cosmic process, the other end of a black hole from a parent universe. This leads to the breathtaking possibility of an entire cosmology built on black and white holes. A black hole in our universe could collapse into a singularity that then rebounds as a white hole, giving birth to an entirely new baby universe in the process, with its own laws of physics and its own arrow of time. Our cosmos might not be the first and only, but merely one link in an infinite chain of universes, each born from the death of a star in a reality that came before it. Now let's connect this to the ultimate sci-fi dream, time travel. If a black hole is a potential entrance to a tunnel through spacetime, could a white hole be the exit? Imagine a traversable wormhole, a bridge connecting 2 points. One end, the black hole, would be the point of entry where matter is pulled in. The other end, the white hole, would be the point of departure where that same matter is violently expelled. If the wormhole also connects 2 different times, then emerging from the white hole could mean arriving in a different era. You would be spit out into the past or the future, a traveler cast out from the cosmic plumbing of spacetime. However, the challenges with this idea are, to put it mildly, monumental. First and foremost, white holes are considered to be profoundly unstable if they can exist at all. General relativity might allow for them mathematically, but the second law of thermodynamics seems to forbid them. A white hole, which increases order by emitting coherent streams of energy, would appear to be decreasing entropy, which goes against the universe's fundamental tendency toward disorder. Most physicists believe that any white hole that somehow formed would almost instantly collapse into a black hole the moment a single speck of dust tried to fall into it, violating its defining no-entry rule. Furthermore, we have absolutely no observational evidence for white holes. We see things falling into black holes, but we have never witnessed a region of space from which matter spontaneously and continuously erupts without any apparent source. Their theoretical nature places them at the very frontier of cosmology, a tantalizing what-if that continues to inspire and challenge our understanding of the cosmos. Yet the promise they hold is immense. They represent the ultimate symmetry in Einstein's universe, a potential key to understanding our own origins, and a theoretical mechanism that completes the circuit of a time traveler's journey, providing the doorway out of the tunnel and into a new age. Now, just when you thought the connection between black holes and time couldn't get any stranger, we venture into the truly bizarre and counterintuitive realm of the very small. To understand our eighth theory, we must first grapple with what Albert Einstein himself called spooky action at a distance, a phenomenon that lies at the heart of quantum mechanics known as quantum entanglement. Imagine you have a pair of magical dice. You take these two dice and without looking at them, you send one on a journey to the farthest galaxy. The instant you roll the die you kept here on Earth and see it land on a 3, you know with absolute certainty that the die in that distant galaxy has also landed on a 3. This isn't just a guess, the outcome is instantaneous. This, in essence, is quantum entanglement. It's a profound connection that links the properties of two particles, like electrons or photons, no matter how far apart they are separated in space. Change the state of one, and the other reacts immediately, seemingly communicating faster than the speed of light. This defies our classical understanding of the universe, where information is supposed to be limited by light's universal speed limit. For decades, this was seen as a strange, if fascinating, quirk of the microscopic world. But what if this mysterious link isn't just a connection through space, but also a bridge through time? This is where our journey takes a truly speculative turn. Some physicists have begun to explore the idea that quantum entanglement might be better understood not as a spatial connection, but as a temporal one. The entangled particles in this view aren't communicating across a vast distance. They are, in a sense, sharing a single existence that transcends our conventional separation of space and time. Their correlation is a fundamental feature of the universe's fabric, a knot tied in the ropes of causality itself. It's as if they were created as a single entity, and that unity persists, making the concepts of here and there, or even now and then, somewhat irrelevant for their shared quantum state. Now bring a black hole into this quantum picture. We've already seen how a black hole's immense gravity warps time to an extreme degree. What if it also has the power to manipulate these delicate quantum connections? One fascinating proposal is that the formation of a black hole could act as a kind of cosmic loom, weaving new threads of entanglement on a monumental scale. As particles and energy are pulled toward the event horizon, the intense gravitational and quantum forces at play could entangle the matter falling in with the Hawking radiation being slowly emitted out. This creates a complex web of quantum links connecting the interior of the black hole with the distant external universe. But here is where the time travel possibility emerges in a new, subtle form. If entanglement truly has a temporal component, then this link forged by the black hole isn't just a connection between inside and outside. It could be a connection between before and after. The information encoded in the infalling matter, which we discussed is stored on the event horizon, could remain quantum entangled with the information that will eventually be carried away by the Hawking radiation billions of years in the future. This creates a quantum bridge across time, where the state of the radiation in the far future is instantly correlated with the state of the matter that fell into the deep past. You couldn't send a message through this bridge in any conventional sense. The information is scrambled and hidden in the noise. However, it establishes a fundamental, non-local connection that ties the fate of the black hole's past directly to its distant future. This suggests that black holes are not just time capsules in a passive sense, but active participants in a cosmic quantum network that stretches across eons. Another, even more speculative idea involves using a pair of entangled particles to probe the flow of time itself near a black hole. Imagine we take one member of an entangled pair, and with great care, we lower it very close to the event horizon of a black hole. Due to the severe gravitational time dilation we explored earlier, time for that particle will be passing incredibly slowly compared to its partner we keep safely far away. If we then perform a measurement on our safe particle, what happens to the entangled connection? Does the correlation hold even though one particle is experiencing a drastically different flow of time? The mathematics suggests it might, but the implications are staggering. It could mean that the quantum link is so fundamental that it operates outside of our standard timeline, connecting two points that are not simultaneous from our external perspective. The particle near the horizon is, in a way, living in our distant future, yet it remains instantly connected to its partner in our present. This creates a scenario where a quantum connection is effectively linking two different times. While this doesn't allow us to send a human back to the age of the dinosaurs, it does hint that the quantum underpinnings of reality might be far more flexible with time than our macroscopic experience would ever suggest. Black holes, in their role as ultimate gravitational engines, might be the only places in the universe where these profound temporal connections can be forged and studied, acting as natural laboratories for the strange interplay between the quantum world and the river of time. The concept of a single, self-consistent timeline is a powerful way to resolve paradoxes, but it demands that our actions are forever constrained by the past. What if the universe offers a more liberating, though infinitely more complex, solution? This brings us to our ninth theory, a radical departure from the Novikov principle that proposes the past isn't a fixed path, but a branching tree of limitless possibilities. We are diving into the many worlds interpretation of quantum mechanics proposed by Hugh Everett in the 1950s. This idea begins not with black holes or relativity, but with the bizarre behavior of the smallest particles. In the quantum realm, a particle like an electron doesn't have a definite position until we measure it. Before observation, it exists in a blurry cloud of probability, a superposition of all its possible states at once. The traditional explanation, the Copenhagen interpretation, says that the act of measurement forces this cloud to randomly collapse into a single, definite reality. Everett found this unsatisfying. He proposed a breathtaking alternative. What if no collapse ever occurs? What if every single possible outcome of a quantum event actually happens? When you measure that electron, the entire universe doesn't choose one state. Instead, it splits or branches into multiple copies. In one new universe, the electron is measured in one position. In another brand new universe, it is measured in a different position. Both outcomes are equally real, they just exist in parallel, non-communicating streams of reality. Now extend this idea beyond a single electron. Every quantum event, from the decay of an atom to the firing of a neuron in your brain, represents a potential branch point. This means that for every decision you've ever made, no matter how small, there is a version of you in a parallel universe who made a different choice. There is a universe where you took that different job, a universe where a different candidate won an election, and yes, a universe where your grandfather never met your grandmother. The many worlds interpretation provides the ultimate escape clause from the grandfather paradox. If you were to travel back in time and prevent your grandfather from meeting your grandmother, you would not be erasing your own history. Instead, the moment you arrive in the past and begin to interact with it, your very presence creates a new branch in the timeline. Your actions cause the universe to split. In the original timeline, your history remains untouched. Your grandparents met, your parents were born, and you were born, eventually leading to your decision to travel back in time. But in the new, freshly created parallel timeline that you have just entered, your grandparents never meet. In that reality, you were never born. This is not a paradox because you are not a native of that timeline. You are a visitor from a parallel branch. You can change the past all you want, but you are only changing the past of this new, alternate universe. Your original home timeline remains pristine and unchanged, its history securely intact. So, how could a black hole facilitate a journey not just through time, but across these parallel worlds? If the many worlds interpretation is correct, then the entire cosmos is a vast, ever-branching multiverse. The immense gravitational forces at work within a black hole, particularly a spinning Kerr black hole, might do more than just warp spacetime. They could potentially twist and stress the very fabric that separates these parallel realities. The ring singularity at the heart of such a black hole might not be a gateway to another point in our own timeline, but a nexus point, a tangled knot where the timelines of different parallel universes briefly touch or overlap. Falling through this ring might not send you to the past of your own world, but to the present or past of an alternate one. You could emerge into a reality where the Roman Empire never fell, where dinosaurs still rule the earth, or where you yourself made a different life choice years ago. The black hole acts as a natural gateway between the branches of the cosmic tree, a portal forged by gravity so extreme that it punches through the barriers between worlds. This also offers a fascinating perspective on the black hole information paradox. When matter falls into a black hole in our universe, where does its information ultimately go? In the many worlds view, the information isn't lost or just encoded on the horizon. It could be transferred or shared across the multiverse. The evaporation of a black hole via Hawking radiation might be the process by which information is not returned to our universe, but redistributed across the infinite ensemble of parallel worlds. The black hole becomes a cosmic router, directing quantum information into the vast network of the multiverse. The implications of this are as dizzying as they are profound. Time travel within this framework is not about changing your own past, but about exploring an infinity of other presents and pasts. There would be no need for the universe to enforce a self-consistency principle because your actions don't create contradictions, they simply create new branches. The responsibility shifts from a cosmic referee to the traveler themselves. You could leave your timeline, but you could never truly return to it unchanged, for your very journey would have created new branches in your absence. The black hole in this grand vision is more than a gateway through time. It is the ultimate crossroads of reality, offering passage into the infinite tapestry of what might have been. But if navigating the chaotic interior of a spinning black hole seems like a daunting prospect, what if we could construct a time machine right here in our own cosmic neighborhood, using principles of physics we already understand? This brings us to our 10th theory, a concept that moves beyond natural cosmic phenomena and into the realm of theoretical engineering on a truly godlike scale. It's the idea of the Tipler cylinder, proposed by the physicist Frank Tipler in the 1970s. Tipler's work demonstrated that you might not need the incomprehensible density of a black hole singularity to bend time into a loop. Instead, his solution to Einstein's equations showed that a sufficiently massive and rapidly rotating object could, in theory, accomplish the same feat. Picture a cylinder, but not just any cylinder. This would be an object of almost unimaginable proportions, potentially millions of miles long, composed of an impossibly dense material and spinning at a significant fraction of the speed of light. The key to its time-bending power lies in this incredible rotation. According to general relativity, any massive rotating body drags the fabric of spacetime around with it, an effect known as frame dragging that we encountered with the Kerr black hole. A simple, slow-rotating planet like Earth produces a barely detectable frame-dragging effect, but a Tipler cylinder, with its immense mass and blistering spin, would twist space-time around itself into a powerful vortex. If you were to travel in a spaceship around this rotating cylinder, following a very specific spiral path, something remarkable would happen. The frame dragging would become so intense that your path through spacetime could curve back on itself, forming a closed time-like curve. By completing a single loop around this man-made whirlpool of spacetime, you could, in theory, return to the exact same point in space, but at a moment in time before you even began your journey. You wouldn't be traveling faster than light. You'd be using the twisted geometry created by the cylinder's rotation to take a shortcut through time itself. Now, the connection to black hole physics is direct and fascinating. A Tipler cylinder is, in essence, a laboratory-scale model of a Kerr black hole's core principles, but without the event horizon and the crushing central singularity. It isolates the frame-dragging effect and amplifies it to its logical extreme, demonstrating that the potential for time loops is a general feature of Einstein's universe, not one exclusive to the most extreme gravitational environments. It shows that the time-warping geometry of a rotating black hole isn't magic. It's a consequence of mass and spin, principles that could, in an ideal world, be replicated. However, this is where we collide with the monumental wall of practical reality. The engineering challenges of building a Tipler cylinder are so vast that they border on the impossible. First, there is the requirement for the cylinder to be infinitely long. Tipler's original mathematical solution demanded this infinity to avoid the formation of singularities and to keep the closed time-like curves contained outside the cylinder itself. In a finite cylinder, the ends would create gravitational and structural instabilities that would likely collapse the entire structure or prevent the necessary spacetime curvature from forming. While some later research suggested a very long but finite cylinder might suffice, the required length is still astronomical. Second, the cylinder must be constructed from a material with the density of a neutron star, but with the structural integrity to withstand its own insane rotational speeds without flying apart. There is no known or theorized material in the universe that could withstand such forces. The electromagnetic and nuclear forces that hold ordinary matter together would be completely overwhelmed by the gravitational and centrifugal stresses. The cylinder would instantly shred itself into a cloud of subatomic particles. So, if building one is forever beyond our reach, could the universe have forged its own natural versions? This is a captivating question. The most likely candidates are, once again, rotating black holes or perhaps their distant, ultra-dense cousins, neutron stars. A neutron star is the collapsed core of a massive star, a city-sized object so dense that a single teaspoon of its material would weigh billions of tons. Many neutron stars rotate at phenomenal speeds known as pulsars, flashing like cosmic lighthouses. Could a pulsar or a pair of orbiting neutron stars create a Tipler-like effect? The frame dragging around a rapidly spinning neutron star is undoubtedly significant, but most models suggest it is still orders of magnitude too weak to produce closed time-like curves. The mass, while immense for its size, is still far less than that of a black hole. The space-time twisting is powerful but not yet a vortex. However, in the complex gravitational dance of a binary neutron star system, where two such ultra-dense objects whirl around each other at incredible velocities, the combined and dynamically changing frame-dragging effects could potentially create regions of highly unusual spacetime geometry. While a full-blown, stable time loop remains highly speculative in such a system, it pushes the boundaries of what might be possible in nature without a full event horizon. The legacy of the Tipler cylinder, therefore, is not as a practical blueprint but as a profound thought experiment. It teaches us that the potential for time travel is woven into the fundamental dynamics of our universe, inherent in the simple, powerful combination of mass and rotation. It demystifies the black hole by showing that its most incredible temporal effects are an extension of physics that operates everywhere, just on a scale we can barely comprehend. The cylinder stands as a testament to human imagination, a challenge from theoretical physics that says the universe's rules might allow for wonders, even if the tools to build them remain forever locked in the realm of pure thought. Stephen Hawking, for all his groundbreaking work on black holes and their potential for time travel, harbored a deep skepticism about its actual possibility. He famously proposed what he called the chronology protection conjecture, a kind of cosmic safety mechanism. His argument was elegant and powerful. The laws of physics, he suggested, simply will not allow time travel to the past because it would violate causality, the fundamental principle that cause must always precede effect. To put it in his own wry terms, he once said, "I have experimental evidence that time travel is not possible. Where are the tourists from the future?" While he said this partly in jest, it points to a serious scientific stance. If closed timelike curves were commonplace, even in the depths of space, why haven't we encountered any evidence of them? Hawking believed that the universe has a built-in defense system, a sort of physics police force that stops paradoxes before they can ever occur. The mechanism for this protection, he theorized, lies in the frenetic energy of the quantum vacuum. We already saw how virtual particle pairs pop in and out of existence. Now, imagine one of these pairs forming on a closed time-like curve. A single photon, for instance, could travel back in time and interact with its earlier self. On a normal timeline, this photon would only exist once, but on a loop, it could pass through the same point in space over and over again, its energy adding up with each pass. The calculations showed that this wouldn't create a gentle glow. It would trigger a runaway feedback loop of unimaginable violence. The energy density of these vacuum fluctuations would rapidly build towards infinity, creating a cataclysmic outpouring of energy that would either destroy the wormhole, the rotating cylinder, or whatever structure was facilitating the time loop long before it could be used. It would be like an audio feedback screech in a microphone, but for reality itself, the universe's way of screaming to shut down the paradoxical system before it rips causality apart at the seams. This isn't just a vague idea. The math from quantum field theory in curved spacetime supports it. When physicists model the behavior of quantum fields on a background geometry that contains a closed time-like curve, the equations often blow up, predicting infinite energy densities that would warp spacetime so severely they would tear the time machine apart. This provides a compelling theoretical backup for Hawking's conjecture. The very quantum effects that might make time travel conceivable through ideas like wormholes are the same effects that would ultimately render it impossible by making the environment infinitely hostile. So, where does this leave black holes? They are, after all, the primary candidates for naturally occurring closed time-like curves. Are they subject to this cosmic censorship, or are they the one glaring exception? This is a central puzzle. The region where closed time-like curves might exist in a Kerr black hole is deep inside, beyond the inner event horizon. Some physicists argue that the chronology protection mechanism would activate precisely at this inner horizon. The buildup of energy from quantum fluctuations could manifest as the inner horizon instability we mentioned earlier, a wall of infinite radiation that would incinerate any traveler and effectively sever the connection to the time-looping region inside. In this view, the black hole's own structure becomes the enforcer of Hawking's rule, using its most violent internal processes to protect the sanctity of causality for the entire external universe. However, others speculate that black holes might be the ultimate loophole. The event horizon itself could act as a shield containing the destructive feedback loop and preventing it from affecting the outside cosmos. From our perspective in the external universe, the time travel region is forever hidden and causally disconnected. The paradoxes might be happening inside, but they can never leak out to influence the timeline we experience. The black hole becomes a sealed chamber where the laws of physics as we know them break down, but whose internal chaos is permanently quarantined. This transforms the black hole from a potential time machine into a cosmic isolation ward, a place where causality is locally violated but globally preserved. Hawking's chronology protection conjecture remains just that, a conjecture. It hasn't been proven as a fundamental law, yet it represents a deeply held belief about the character of our universe, that it is constructed in such a way as to make the past immutable and paradox-free. It suggests that while we can bend time, we can never break it, and that the cosmos will always find a way, whether through infinite energy or hidden horizons, to keep history safe from meddlers. If black holes can evaporate and scramble information through Hawking radiation, what secret ledger does the universe keep to ensure nothing is truly lost? The answer lies in one of the most profound connections ever made in theoretical physics, linking the invisible world of thermodynamics to the stark reality of gravity. The story begins with a young physicist named Jacob Bekenstein, who in the 1970s made a startling proposition. He suggested that black holes are not just simple objects, they must possess a property called entropy. Entropy is essentially a measure of disorder or randomness in a system. It's the reason ice cubes melt in a warm drink, spreading out the molecules, and why it's far easier to make a mess than to clean one up. The second law of thermodynamics states that the total entropy of the universe always increases. Things naturally tend toward greater disorder. Bekenstein realized that when you throw something, anything, into a black hole, you are removing all of that object's entropy from the visible universe. A cup of coffee, a book, a complex spacecraft, all of their intricate, disordered information vanishes behind the event horizon. To an outside observer, it seems the total entropy of the universe has just decreased, which would violate the cherished second law. Bekenstein's brilliant insight was that the black hole itself must compensate. It must have its own entropy, and that entropy must increase by an amount greater than the entropy of the object it consumed, preserving the universal trend toward disorder. This meant that a black hole, an object seemingly defined by its simplicity, was actually the universe's ultimate reservoir of chaos and information. Stephen Hawking initially disliked this idea as it challenged the conventional view of black holes, but his own subsequent work on Hawking radiation not only confirmed it but gave it a stunning numerical precision. He calculated that a black hole's entropy is not just a vague concept, it is exactly proportional to the surface area of its event horizon. This is a deeply counterintuitive result. In every other system we know, entropy is proportional to volume. A large box can contain more disordered arrangements of atoms than a small box, but for a black hole, the entropy, the total information it contains, is tied to its two-dimensional surface area, not its three-dimensional volume. It's as if every book, every star, every bit of matter that falls in is not compressed into the tiny singularity, but is instead smeared out and painted onto the inner wall of the event horizon like a cosmic mural. This discovery was the first crucial step toward the holographic principle, an idea that radically reimagines the nature of reality itself. The principle suggests that our perception of a three-dimensional universe with depth and volume might be an illusion, a projection from a two-dimensional surface that contains all the information needed to describe it. Think of a standard hologram like the one on your credit card. It's a flat, two-dimensional piece of plastic, but when light shines on it, it projects a full, three-dimensional image. The holographic principle applies this same logic to the entire cosmos. The event horizon of a black hole acts as that two-dimensional surface, a vast cosmic hard drive where the quantum bits or qubits that define everything within the black hole's volume are stored. Every particle, every force, every vibration that falls in is translated into a complex code on this spherical surface. Now, how does this breathtaking idea connect to time travel? The flow of time is intimately linked to the increase of entropy. We remember the past and not the future because the past was a state of lower entropy. The holographic principle tells us that this flow, this arrow of time, is not a fundamental property of the deep volume of space, but rather an emergent feature arising from the way information is processed and rearranged on the underlying two-dimensional surface. If the fabric of our reality is truly a holographic projection, then manipulating the projector could, in theory, manipulate the projection including its timeline. Imagine that the information encoding your present moment is stored on a specific part of this cosmic film. If you could somehow access the projector and deliberately rewind or fast-forward that specific strip of data, you could, in essence, change what is being projected. For a conscious being, this wouldn't mean building a machine to travel through space, but finding a way to interface directly with the source code of reality. You wouldn't be moving your body to the Cretaceous period. You would be reprogramming the hologram so that your conscious experience is projected into that era. This is a form of information-based time travel where the journey is not physical but experiential, a recalibration of the data stream that constitutes your reality. Of course, the practical barriers are beyond astronomical. The amount of information on even a small black hole's event horizon is staggering, and the computational power needed to decode it, locate a specific moment in history, and reconfigure it to include your own conscious data is unimaginable with any technology we can conceive. It's less like engineering and more like rewriting the operating system of the universe with perfect comprehension. Yet, as a theoretical possibility, it offers a completely different paradigm. It suggests that time travel might not be about navigating wormholes or surviving spinning singularities, but about achieving a god-like understanding of the informational substrate from which time itself emerges. The black hole, in this view, is not a gateway but a teacher. It shows us that the universe might fundamentally be a vast and complex computation, and that the river of time is the stream of its output. To travel in time would be to learn to read the source code, and in doing so, to choose which part of the program to run. We have ventured into the quantum realm and wrestled with the nature of information, but let's now return to one of the most direct and visceral consequences of Einstein's gravity, an effect so powerful it brings time itself to a screeching halt from a certain point of view. This is the ultimate expression of gravitational time dilation at the event horizon of a black hole. You'll recall that gravity slows time. The closer you are to a massive object, the slower your clock ticks compared to someone in a weaker gravitational field. Now amplify this effect from the slight ticking difference on a mountaintop to the unimaginable gravitational grip of a black hole. The event horizon is the point of no return, the boundary where the escape velocity equals the speed of light. As an object falls toward this boundary, an outside observer would witness something truly bizarre. The falling object, whether it's a probe or a person, would appear to slow down dramatically. Its descent would become a gradual, agonizing crawl. As it gets closer and closer to the event horizon, the light coming from it would become redder and dimmer, stretched by the immense gravity into longer, lower energy wavelengths, a phenomenon known as gravitational redshift. From the perspective of someone watching from a safe distance, the object would never actually cross the event horizon. It would appear to approach asymptotically, freezing in place just at the boundary, fading to infrared, and then vanishing from sight entirely as the light becomes too faint to detect. In a very real sense, from our external reference frame, time for that falling object has stopped completely at the horizon. It's as if the last second of its existence from our point of view is stretched out to infinity. This leads to a profound and troubling question. If time is frozen at the horizon for outside observers, does that mean the event horizon is a wall of frozen corpses, all the things that ever fell in, eternally stuck in their final moment? The resolution to this paradox lies in the fact that there is no single, universal now in our universe. Time is personal. what an outside observer sees is not what the falling individual experiences. For the person brave or unfortunate enough to be crossing the horizon, their local time continues to pass entirely normally, at least initially. There is no flashing neon sign, no sudden jolt. If the black hole is large enough with a less intense tidal force at its horizon, the crossing could be utterly uneventful. You would simply fall through the mathematical boundary, unable to stop or turn back, with the entire future history of the universe unfolding in a blinding flash of light behind you. This is the twin paradox taken to its absolute cosmic extreme. Imagine two identical twins. One, the stay-at-home twin, remains on a safe observation platform far from the black hole. The other, the adventurous twin, volunteers to take a journey directly toward the event horizon. As the adventurous twin falls, the stay-at-home twin watches through a powerful telescope. They see their siblings' movements slow to a standstill, their image redden and fade. From the stay-at-home twin's perspective, their adventurous sibling never dies. They are just frozen in time at the edge of forever. Meanwhile, for the adventurous twin falling inward, their own watch ticks forward second by second. They see the outside universe not frozen but spectacularly accelerated. The light from stars' blue shifts ahead of them as the frequency of incoming light is compressed. They would witness the stars evolving, burning out, and new ones being born in a frantic rush. Galaxies would collide and merge in a matter of moments. The entire future history of the cosmos, spanning billions of years, could flash before their eyes in the short time it takes them to cross the horizon and continue their inevitable plunge toward the central singularity. In this way, crossing the event horizon of a supermassive black hole is, in a very real sense, a one-way trip to the extreme future. The traveler isn't moving forward in time within their own reference frame, but they are effectively leaping ahead in the timeline of the external universe. By the time they cross the boundary, the outside cosmos may have aged by eons. There is no return from this kind of journey. You could not cross the horizon, wait a minute, and then pop back out to see what the universe looks like in a trillion years. The geometry inside the horizon is such that all possible paths lead relentlessly toward the center, toward the singularity. This makes the black hole the universe's most definitive and brutal time capsule. It doesn't just slow time, it severs a traveler from the entire causal past of the universe, delivering them to a point in the cosmic future from which there is no possible communication or return. It is the ultimate expression of time dilation, not as a subtle effect, but as a fundamental and catastrophic disconnection from the flow of time as the rest of the universe experiences it. Now, let's contemplate a puzzle so twisted that it challenges the very notion of where things come from. Imagine you are a time traveler with a love for classical music. You travel back to the 18th century and meet a young, struggling composer named Wolfgang Amadeus Mozart. Eager to help, you pull out your phone and play him a symphony from your own time, a masterpiece he has never heard. He listens, utterly captivated, and then writes it down note for note, publishing it under his own name. The symphony becomes one of his most celebrated works, passed down through the centuries until you eventually hear it in your own time, decide it's your favorite, and take it back to give to him. So, who really composed that symphony? Did Mozart write it, or did you? The music exists in a perfect loop with no discernible origin. It was never created, only endlessly recycled. This is the essence of the bootstrap paradox, a causal loop where an object, a piece of information, or an event is sent back in time, becoming the very cause of itself in the future. It's a closed cycle with no beginning, an effect that becomes its own cause, trapping reality in a logical Möbius strip. The term bootstrap comes from the absurd idea of pulling yourself up by your own bootstraps, an impossible feat that captures the sheer strangeness of an object or idea that literally lifts itself into existence from nothing. Another classic example involves the works of Shakespeare. What if a time traveler, armed with a complete collection of the bard's plays, went back to Elizabethan England and handed the manuscripts to a young William Shakespeare, who then simply copied them out and claimed them as his own. The plays would never have been originally authored by anyone. Their existence would be a closed loop in time, with Shakespeare merely being the agent of their transmission, not their creation. This paradox isn't just a fun brain teaser, it strikes at the heart of causality and creation. In our everyday world, we operate on the assumption that everything has a cause that came before it. The bootstrap paradox shatters that assumption, presenting a reality where things can simply be without a point of origin. So, how could the terrifying physics of a black hole enable such a reality-defying loop? The connection lies, once again, in the warped geometry of closed timelike curves. We've discussed how the intense frame dragging of a rotating Kerr black hole could, in theory, twist spacetime so severely that a path could loop back and connect to its own past. If such a path were stable and traversable, it would be the ultimate physical mechanism for a bootstrap paradox. An object or a signal could travel along this curve, arriving at a point in its own past. It could then be discovered and sent back again, completing the cycle. The black hole wouldn't create the object, it would simply provide the cosmic racetrack, the twisted plumbing of spacetime that allows information or matter to chase its own tail for all eternity. Within the black hole's inner sanctum, the distinction between cause and effect could become utterly meaningless. But does this mean the universe would allow such a logical absurdity to exist? This is where quantum mechanics might step in with its own set of rules. One potential resolution comes from the inherent unpredictability of the quantum world. Imagine a bootstrap loop involving a single quantum particle, like an electron in a specific spin state. If that particle were sent back in time to become its own ancestor, the loop would require its quantum state to be perfectly consistent at every point. However, quantum mechanics is fundamentally probabilistic. The act of measuring the particle's state could cause its wave function to collapse randomly. This introduces a tiny but crucial element of randomness that could break the perfect consistency of the loop. The particle might return to the past in a slightly different state than it was originally, preventing the paradox from forming a perfectly stable, self-consistent cycle. The universe, through quantum uncertainty, might simply refuse to be trapped in such a deterministic knot. Another perspective comes from the many worlds interpretation. If you were to take a book back in time and give it to its author, you wouldn't be creating a paradox in your original timeline. Instead, your act of delivering the book would cause the universe to branch. In the new parallel timeline, the author receives the book and publishes it. That book then becomes part of that new reality's history. The information has an origin, it came from a different universe. The bootstrap is broken because the loop isn't closed. It's open across the multiverse, with the information simply hopping from one branch of reality to another. From the author's perspective in the new timeline, the book seemingly appeared from nowhere, but from a multiversal viewpoint, it was imported. Finally, there is the daunting idea that the Novikov self-consistency principle we discussed earlier would apply here with full force. The principle asserts that the only possible time loops are those that are perfectly self-consistent. In the case of the bootstrap paradox, this wouldn't be a paradox at all, but a fundamental feature of that timeline. The symphony always came from the future. There was no first version. Mozart's role was always to transcribe, not to compose. The timeline is simply built that way, with the mysterious origin of the music being an immutable, baked-in fact of that universe's history. The loop is stable because it has to be. The laws of physics would forbid any variation. The black hole, in this view, wouldn't be a source of chaos, but a guardian of a very strange but perfectly consistent type of history where some things have no beginning, only an eternal, recycled existence. It forces us to ask a deeply philosophical question. In a universe where time is flexible, is an origin story even necessary? Or can reality accommodate things that are, in a very real sense, timeless? But what if we could achieve the effects of a black hole's gravity without the danger of actually falling into one? What if we could command the fabric of spacetime itself, telling it how to bend to our will, creating a gravitational wave that we could surf across the cosmos? This brings us to a theory that feels like it's pulled from the most optimistic visions of science fiction, yet is grounded in the rigorous math of general relativity: the Alcubierre warp drive, proposed by physicist Miguel Alcubierre in 1994. The fundamental problem with interstellar travel, and by extension any form of practical time travel, is the cosmic speed limit, the speed of light. Nothing with mass can ever reach or exceed this speed. But Alcubierre had a brilliant insight. Einstein's equations don't forbid spacetime itself from expanding or contracting at any speed. The Alcubierre drive cleverly sidesteps the light speed barrier by not moving the ship through space, but by moving space itself around the ship. Imagine a surfer riding a wave. The surfer isn't paddling frantically through the water. Instead, the wave is carrying them forward. Now, replace the ocean with the fabric of spacetime. The Alcubierre drive would create a warp bubble, a local distortion of spacetime that encloses the spacecraft. Behind the ship, spacetime would be expanded, pushing the point of origin far away. In front of the ship, spacetime would be radically contracted, bringing the destination incredibly close. The ship itself sits comfortably in a flat, undisturbed region of spacetime within this bubble, experiencing no acceleration forces, no time dilation from high velocity, and no violation of the local speed of light. It's as if you are standing still on a moving walkway that is itself sliding across a landscape that is folding and unfolding ahead of you. The connection to black hole physics is direct and profound. The immense gravitational field of a black hole contracts spacetime in its vicinity to an extreme degree, creating a deep well. The Alcubierre drive essentially replicates a specific, controlled aspect of this phenomenon. The region of contracted spacetime in front of the bubble is analogous to the warped space just outside a black hole's event horizon, where the fabric of the cosmos is pulled taut. The expanding region behind the bubble is like the inverse, a kind of artificial white hole effect pushing spacetime outward. In essence, the warp drive creates a pocket of manipulated gravity that mimics and even surpasses the most extreme curvature found in nature, but does so in a way that is theoretically survivable for its passengers. Now for the truly mind-bending part: could this manipulation of spacetime also allow for time travel? The mathematics suggests a tantalizing possibility. Because the warp bubble is moving through spacetime faster than light from an external perspective, it would also be traveling along what physicists call a space-like trajectory. In the geometry of relativity, such paths can, under the right conditions, connect two points in spacetime that would normally be separated in time as well as space. A ship using an Alcubierre drive to travel to a distant star and back might not only break the light barrier but also the time barrier. Upon returning to Earth, the crew could find that they have arrived back home before they even left, effectively traveling into their own past. This would create a closed timelike curve, just like the ones we explored inside rotating black holes, but this time engineered by human technology. You wouldn't need to navigate the violent interior of a Kerr black hole. You could potentially create your own time loop right here in our cosmic neighborhood. However, this breathtaking vision crashes headlong into some of the most formidable physical barriers ever conceived. The first and most famous problem is the energy requirement. Early calculations for a modest warp bubble large enough to hold a spacecraft were staggering, requiring negative energy equivalent to the mass energy of Jupiter or even more. Later refinements have suggested ways to reduce this, perhaps to the mass energy of something like the Voyager probe, but that still represents an amount of energy far beyond our current or foreseeable capabilities to produce and, more importantly, to control. The second and even more fundamental problem is the need for exotic matter. To create the warp bubble, you don't just need a colossal amount of energy, you need a very specific kind of energy with a negative energy density. This exotic matter would have to exhibit negative gravity or negative pressure to push spacetime apart behind the ship and pull it together in front. As we discussed with wormholes, while quantum field theory allows for the existence of negative energy densities in tiny amounts, as seen in the Casimir effect, the idea of manufacturing and containing the vast quantities needed for a macroscopic warp drive remains a monumental and perhaps insurmountable challenge. Furthermore, there are serious theoretical concerns about the stability of the warp bubble and potential catastrophic effects when it decelerates. Some models suggest that particles and radiation would build up at the front of the bubble, and when the drive is turned off, this accumulated energy would be released in a devastating blast, sterilizing the destination planet. There are also questions about whether the crew inside could even control or steer the bubble, as the region where the warping occurs is causally disconnected from the flat space inside. The Alcubierre drive stands as a testament to the power of human imagination applied to the laws of physics. It shows us that the universe's rulebook might contain the instructions for building a starship, even if the tools and materials required are currently and may forever be out of our reach. It bridges the gap between the natural time warping power of black holes and the dream of commanding that power for ourselves, offering a vision of a future where we are not just passengers on the river of time, but the architects of its flow. Our journey through the theories of time and black holes has taken us from the vast, warped geometry of general relativity down into the strange, probabilistic realm of quantum mechanics. But these two pillars of modern physics stand in a state of uneasy truce. General relativity masterfully describes the cosmos on large scales, the dance of planets, the bending of light, and the curvature of spacetime around black holes. Quantum mechanics, with equal brilliance, governs the bizarre world of the impossibly small, the behavior of atoms and particles. Yet, when we try to apply both theories to the same place, namely the center of a black hole or the first moment of the Big Bang, the mathematics shatters into nonsense, producing infinities that signal a complete breakdown of our understanding. This great disconnect brings us to the holy grail of theoretical physics, the quest for a theory of quantum gravity, a single framework that would seamlessly weave these two master narratives into one. And it is within this quest that we find a theory about the very fabric of reality so radical, it suggests that spacetime itself might not be the smooth, continuous stage we imagine, but a churning, effervescent foam. To grasp this, we need to venture down to the smallest possible scales, to a realm known as the Planck length. This is an almost unimaginably tiny distance, about 1 trillion times smaller than a proton. At this scale, the universe as we know it ceases to be well-behaved. The bedrock principle of quantum mechanics, the Heisenberg uncertainty principle, tells us that we can never know both the exact position and the exact momentum of a particle. This uncertainty also applies to energy. For vanishingly brief moments, vast amounts of energy can spontaneously burrow into existence from nothing, so long as they vanish again almost instantly. Now apply this quantum frenzy not to particles, but to the fabric of spacetime itself. According to Einstein, energy and mass warp spacetime. So if there are wild, random fluctuations in energy at the Planck scale, then spacetime itself must be fluctuating wildly. It would be a seething, turbulent foam with tiny wormholes constantly blinking in and out of existence, and the very concepts of here and there losing all meaning. Space and time at this fundamental level would not be smooth and continuous, but grainy, discrete, and dynamically changing. This is the theory of spacetime foam, a concept first proposed by the legendary physicist John Wheeler. Imagine the surface of the ocean. From an airplane, it looks like a serene, flat sheet. But if you were a tiny insect floating on that surface, you would experience a chaotic world of bubbling foam with waves constantly forming and collapsing. Our experience of smooth, four-dimensional spacetime is like the view from the airplane. The reality at the quantum gravitational level is the frantic, foamy experience of the insect. This foam isn't made of bubbles in a substance. It is the substance. The very geometry of reality is in a perpetual state of quantum turmoil. Now, how could a black hole, the most massive object we know of, possibly reveal such an infinitesimally small phenomenon? The answer lies in the fact that black holes are the ultimate squeezers. They take vast amounts of matter and compress it into an incredibly tiny volume, pushing physics to its absolute limits. The event horizon of a black hole is the boundary where gravity is so strong that not even light can escape. But what happens to this boundary when we view it through the lens of quantum gravity? The tremendous gravitational field at the horizon should amplify the tiny quantum fluctuations of the spacetime foam. The perfectly smooth, classical surface described by general relativity would, in reality, be a roiling, fuzzy boundary, its precise location shimmering and uncertain due to the quantum foam frothing just beneath it. Some theorists suggest that this foamy structure could even affect the way black holes evaporate through Hawking radiation. The radiation isn't emitted from a perfectly sharp surface, but from this turbulent quantum layer, potentially leaving subtle imprints on the radiation itself that, if we could ever detect them, would be a direct signature of quantum gravity at work. Furthermore, the mind-bending holographic principle we discussed earlier, which states that all the information within a black hole's volume is encoded on its two-dimensional surface, finds a natural home in the concept of spacetime foam. The hologram's pixels, its fundamental bits of information, could be manifestations of this underlying foam, with each quantum fluctuation representing a single bit in the cosmic code. This leads us to the ultimate speculative question. If spacetime is a dynamic foam at its heart, could we learn to manipulate it, not just to travel through space, but through time? The idea hinges on the transient wormholes that are thought to be a key feature of the foam. These are not the stable, traversable tunnels of science fiction. They are microscopic, chaotic, and ephemeral, forming and vanishing in far less than a blink of an eye. But what if a truly advanced civilization could find a way to capture one of these fleeting wormholes? The energy required to pry one open and stabilize it, pinning down a frothing bubble of spacetime, would be beyond colossal, perhaps requiring the entire energy output of a star. However, if it were possible, you would have in your hands a direct bridge between 2 points in spacetime. By manipulating the geometry of this stabilized wormhole, perhaps by moving one of its mouths at relativistic speeds or placing it in a powerful gravitational field, you could, in theory, turn it into a time machine. One end of the wormhole could be made to experience time much more slowly than the other, creating a time difference between the two portals. Then, stepping through one end would deposit you not just in another location, but in another time. The spacetime foam in this vision is not just the quantum bedrock of reality. It is a plenum of raw, untapped potential, filled with incipient time machines waiting to be harnessed. Of course, the obstacles are not merely technological, they are foundational. We do not yet have a complete theory of quantum gravity to tell us if such manipulation is even allowed by the laws of physics. The energy densities involved might always be prohibitive, or the very act of stabilizing a wormhole might trigger a catastrophic instability, a feedback loop of energy that reinforces Hawking's chronology protection conjecture and destroys the wormhole. Yet, the theory of spacetime foam offers a profound shift in perspective. It suggests that the smooth, reliable flow of time we experience is an emergent illusion, a calm average over a hidden, chaotic quantum reality. To travel through time would not be to fight against the grain of the universe, but to learn to swim within its truest, most fundamental currents. The black hole, by magnifying these quantum effects to an observable scale, might one day be the key that unlocks this deeper layer of existence, revealing a cosmos that is, at its heart, a bubbling sea of temporal possibility. The classic grandfather paradox has haunted the imagination of scientists and storytellers for generations, presenting a seemingly insurmountable logical barrier to traveling into the past. The premise is starkly simple. If you journey back in time and prevent your own grandfather from meeting your grandmother, you would ensure your own birth never happens, which raises the question of how you could have ever existed to make the journey in the first place. It's a perfect causal loop of contradiction, a riddle that appears to prove time travel is an impossibility. But what if this paradox is not a death sentence for the concept, but merely a challenge to our classical way of thinking? Modern physics, particularly when viewed through the extreme lens of black hole physics, offers several breathtaking ways the universe might resolve or outright avoid this fundamental problem. One of the most compelling solutions is the idea of multiple timelines, which we touched on with the many worlds interpretation. In this framework, the moment you arrive in the past and take an action that would alter established history, you don't rewrite your own timeline. Instead, your presence causes the universe to branch, creating a new, parallel reality. In this new timeline, your grandfather never has children and you are never born. But this isn't a paradox because you are not a native of this new branch. You are a visitor from the original timeline where your grandfather did meet your grandmother and you were born. Your personal history remains perfectly intact and unchanged. You can change the past all you want, but you are only changing the past of a newly created universe. From the perspective of this new reality, you are a mysterious stranger with no origin, but from a multiversal viewpoint, your history is secure. This provides a clean, elegant escape from the paradox, but it requires accepting an infinitely branching cosmos. Now consider how a black hole might facilitate this. If the ring singularity of a spinning Kerr black hole acts as a nexus point where different parallel realities touch, then falling through it might not send you to the past of your own universe, but to the past of an alternate one. Your journey would be an excursion across the multiverse, not a voyage within a single timeline. This transforms the black hole from a potential time machine into a gateway between worlds, a natural mechanism that inherently avoids the grandfather paradox by ensuring you never interact with your own actual past. A second and philosophically very different solution is the Novikov self-consistency principle. This approach asserts that the universe is fundamentally constrained to prevent paradoxes. It posits that if time travel to the past is possible, then the timeline is a single, immutable, and self-consistent loop. Your actions in the past were always a part of that past. You cannot change history because you are already a component of it. Applying this to the grandfather paradox, you might travel back with the intent to interfere, but the laws of physics would conspire to make you fail. Your gun would jam, you would slip at the crucial moment, or a sudden change of heart would stop you. Perhaps your very attempt is what indirectly causes your grandparents to meet. Maybe your disruptive presence in their town leads them to cross paths in a way they never would have otherwise. Your journey back in time doesn't create a new future. It ensures the future that already includes your journey unfolds exactly as it always has. In the context of a black hole, this principle suggests that the violent instabilities and radiation at the inner horizon might be the universe's brutal enforcement mechanism. Any traveler attempting to use a closed timelike curve to create a paradox would be met with a wall of infinite energy, a physical barrier that eliminates the possibility of contradictory actions. The black hole's own internal physics becomes the guardian of cosmic consistency, ensuring that any journey through time is a ride on a predetermined track with no switches or diverging paths. Then there is the most unsettling and speculative resolution, quantum suicide. This idea emerges from the many worlds interpretation but applies it at a deeply personal level. Imagine a scenario where you travel back in time and point a gun at your grandfather. The moment you pull the trigger, the universe splits. In one branch, the gun fires and you succeed in altering the past. In that branch, you cease to exist. However, from your own subjective first-person perspective, you only ever experience the branches of reality in which you are alive. Therefore, you would only ever find yourself in the branches where the gun miraculously jams, a bystander intervenes, or you simply miss. No matter how many times you try, from your point of view, you will always fail. It would appear as though a strange, protective fate is shielding you and the timeline, when in reality, you are simply unaware of the countless branches where you did succeed and vanished. Your conscious experience is tethered to the versions of reality where your existence remains consistent. If a black hole's interior does contain a chaotic foam of quantum possibilities, entering it could be the ultimate test of this theory. A traveler might attempt an act that could create a paradox, and from their own perspective, they would always emerge unscathed, their timeline intact, blissfully ignorant of the other versions of themselves that were erased by their own actions. The black hole becomes a quantum filter, a natural experiment in existential probability. Ultimately, the grandfather paradox forces us to confront what we believe about causality, identity, and the very structure of reality. Is the past a single, unchangeable record? Is it one thread in an infinite tapestry of parallel histories? Or is our conscious experience a fluke, a single path we walk while an infinity of other versions of ourselves take different turns? Black holes, as the universe's most extreme environments, provide the theoretical arenas where these questions are no longer just philosophical musings. They are physical possibilities tested against the most ferocious gravitational and quantum forces nature can muster. The solutions to the paradox suggest that the universe is far more clever and complex than our simple notions of cause and effect, offering escape hatches from logical dead ends that we are only just beginning to map. But just when we think we're beginning to understand the strange quantum fate of information at a black hole's edge, a truly shocking idea emerged that threatened to turn everything on its head. This is the theory of the black hole firewall, a concept so radical it suggests the event horizon might not be the smooth, uneventful gateway described by general relativity, but a searing wall of pure energy, a cosmic kill zone that would instantly incinerate anything trying to cross. The story of the firewall begins with a question that seems almost comical but is deadly serious in the world of theoretical physics. If you fall into a black hole, what do you feel when you cross the event horizon? For decades, the answer from general relativity was clear: nothing. You would feel no sudden jolt, no dramatic barrier. This principle is known as the no-drama conjecture. Because you are in free fall, you would experience the local laws of physics as you always do. The horizon is a mathematical boundary, not a physical wall. But in 2012, a team of physicists including Ahmed Olmary, Donald Marolf, Joseph Polchinski, and James Sully, often referred to by the acronym AMPS, pointed out a devastating conflict. They argued that preserving the no-drama scenario while also ensuring that information is not lost from the universe as required by quantum mechanics leads to an irreconcilable paradox. To understand their logic, we need to follow a thought experiment involving three characters: Alice, Bob, and a very old black hole. Imagine Alice is brave enough to jump into a black hole. Her friend Bob stays far outside, observing from a safe distance. Now, this black hole is very old. It has been emitting Hawking radiation for a long time. According to the idea of information preservation we discussed earlier, the Hawking radiation being emitted now must be entangled with the radiation that was emitted in the far past. This is a fundamental quantum link. The early radiation and the late radiation are connected. However, for information to be preserved without a paradox, the late radiation must also be entangled with the particles that fell into the black hole with Alice. This is where the problem arises. In quantum mechanics, there's a fundamental rule called the monogamy of entanglement. A single quantum bit or qubit cannot be fully and completely entangled with two different systems at the same time. It's like a marriage. You can't be perfectly, maximally entangled with two different partners. The late radiation cannot be faithfully entangled with both the early radiation and with Alice's infalling particles. Something has to give. The AMPS team argued that to save quantum mechanics and prevent information from being lost, the entanglement between the early and late radiation must be preserved. But that means the connection between the late radiation and Alice's particles must be severed. And the most violent, dramatic way for that quantum link to be broken is for Alice to encounter a tremendous wall of energy right at the event horizon, a firewall. She wouldn't pass smoothly into the black hole. She would be vaporized the instant she touched the horizon. This is a staggering conclusion. The event horizon, the gateway to the black hole's interior, becomes the most energetic and destructive place in the entire universe. The no-drama principle of general relativity is sacrificed to save the purity of quantum mechanics. Now, what would this mean for the dream of time travel? If the firewall theory is correct, it would be an absolute and definitive barrier. Any attempt to use the extreme time dilation at the horizon or to venture inside to find closed time-like curves would be instantly and utterly futile. You could not get close. The horizon would be a blazing inferno, a boundary of pure chaos that destroys all information and any potential traveler long before they could exploit the warped spacetime within. The black hole would be a cosmic fortress, its time-bending secrets guarded by an impassable wall of fire. The very mechanism that might allow for journeys through time would be permanently locked behind a shield of annihilation. However, the firewall proposal is deeply controversial and has sparked a fierce debate in the physics community. Many theorists find the idea of a fundamental breakdown of general relativity at the horizon deeply unsatisfying. After all, Einstein's theory has passed every test with flying colors. If it fails at the one-way door of a black hole, where else might it fail? This has led to a search for alternative resolutions that can preserve both the no-drama principle and the unitarity of quantum mechanics. One fascinating alternative suggests that the problem lies in assuming that the interior of the black hole and the exterior Hawking radiation are two separate, distant things. What if they are not so separate? The concept of complementarity, first proposed by Leonard Susskind, offers a way out. It suggests that the experience of Alice falling in and the observations of Bob outside are both correct, but they are complementary descriptions of reality that can never be compared. From Alice's perspective, she falls smoothly through the horizon, experiencing no firewall. From Bob's perspective, he sees her hit a searing wall of energy and get burned to a crisp. These are not contradictory facts because no single observer can ever have access to both sets of information. The moment Alice crosses the horizon, she is causally disconnected from Bob forever. There is no experiment, no message, no signal that can ever connect Bob's observation of a crispy Alice with Alice's own experience of a safe passage. The universe, in a sense, doesn't need to be consistent across this ultimate divide. Another, even more mind-bending idea is that of ER equals EPR. This is a conjecture that connects two seemingly unrelated concepts from physics. ER stands for Einstein-Rosen bridges, which we know as wormholes. EPR stands for Einstein, Podolsky, and Rosen, the physicists who first highlighted the strange phenomenon of quantum entanglement. The ER equals EPR proposal suggests that what we perceive as a pair of entangled particles are not two distinct objects connected by a mysterious spooky force, but are actually two ends of a microscopic wormhole. They are physically connected by a tiny bridge in spacetime. Now apply this to our black hole paradox. The Hawking radiation particles outside the black hole are entangled with the particles inside the black hole. If ER equals EPR is correct, then they are not just spiritually linked. They are physically connected by a vast, complex network of microscopic wormholes. In this view, there is no sharp, local firewall because the interior of the black hole and the exterior radiation are not separate. they are part of one connected geometric structure. The information doesn't need to be transmitted or scrambled. It is simply on the other end of a wormhole. Alice falling in wouldn't hit a wall because she is, in a very real geometric sense, already connected to the outside. This doesn't make the journey safe. The traditional dangers of the singularity still await, but it potentially removes the need for a violent, paradoxical boundary at the horizon itself. The debate over firewalls is far from settled. It represents the growing pains of a field trying to reconcile two fundamentally different descriptions of reality. Whether the horizon is a serene passage or a destructive inferno has profound implications not just for information and black holes, but for the very nature of spacetime. It forces us to ask what we are willing to sacrifice: the elegant geometric certainty of Einstein's gravity, or the bizarre probabilistic rules of the quantum world. For the would-be time traveler, the answer determines whether a black hole is the ultimate adventure or the final dead end. We have wrestled with wormholes and warped spacetime, confronted firewalls and quantum foam, but our next theory introduces a form of matter so strange it defies the very definition of equilibrium. Imagine a crystal. We're all familiar with their spatial structure, the beautiful, repeating lattice of atoms in a diamond or a snowflake, a pattern that stretches across space. Now stretch your imagination and picture a structure that does the same thing not in space but in time. This is the mind-bending concept of a time crystal. Proposed by Nobel laureate Frank Wilczek in 2012, a time crystal is a quantum system in its lowest possible energy state, yet it exhibits motion that is perfectly periodic and persistent, repeating itself over and over in time without ever consuming any energy. Think of it as a clock that ticks forever without ever being wound, an eternal motion machine not of the macroscopic world, which is impossible, but of the quantum realm where the rules are different. In a regular crystal, the spatial symmetry is broken. The atoms are arranged in a pattern that doesn't look the same in every direction, which is why a snowflake has 6 unique arms. In a time crystal, it's time translation symmetry that is broken. In an empty, featureless void, one moment is identical to the next. That's time translation symmetry. But a time crystal picks out a specific rhythm, a periodic beat, making it so that moments separated by this specific time interval are identical, but the moments in between are not. It's a structure that, in its ground state, is fundamentally and perpetually out of sync with the uniform flow of time itself. The creation of time crystals in controlled laboratory settings has been one of the most exciting developments in quantum physics in recent years. Scientists have built them using complex systems like chains of trapped ions or dense diamonds with numerous nitrogen vacancy defects. By periodically poking these systems with a laser, like pushing a child on a swing at a set frequency, they can force the system into a rhythmic response. The truly bizarre part is that the time crystal then begins to oscillate at a different, slower period than the laser's push. It establishes its own intrinsic temporal rhythm, a stubborn beat that persists even as the external driving force is varied, a signature of a stable, non-equilibrium phase of matter. So, what could these bizarre quantum objects possibly have to do with the colossal gravity of black holes? The connection lies in the extreme environments these cosmic giants create. The vacuum of space around a black hole is not empty and placid. It is a maelstrom of quantum activity shaped by immense tidal forces and frame-dragging effects. Theorists like Norman Yau and others have speculated that the powerful periodic gravitational influences near a black hole could act as a natural driver, much like the laser in the lab. A swirling disk of superheated plasma, known as an accretion disk, orbits a black hole at velocities approaching the speed of light. The matter in this disk is subjected to a regular, rhythmic pulse of immense gravity and radiation. This could, in theory, provide the exact conditions needed to nudge a suitable quantum system, perhaps a cloud of particles or a specific quantum field near the event horizon, into a time crystalline phase. In this view, the black hole doesn't just warp space, it could also imprint a persistent temporal pattern onto the very fabric of the quantum fields in its vicinity. The black hole and its accretion disk become a cosmic metronome, setting a beat so powerful it forces the surrounding vacuum to dance to a new perpetual rhythm. This leads us to the most profound potential application: stable time loops. Our previous discussions of closed timelike curves inside Kerr black holes were plagued by instability, the potential for infinite energy buildup and catastrophic feedback loops. A time crystal, by its very nature, represents a state of matter that is stable and periodic in time. What if such a structure could be used not just to mark time, but to structure it? Imagine a wormhole that is inherently unstable, its throat threatening to snap shut. Now, line the throat of this wormhole with a time crystalline material. The persistent, self-sustaining oscillation of the time crystal could, in theory, act as a stabilizing agent. It would provide a constant, rhythmic reinforcement to the spacetime geometry, preventing the wormhole from collapsing. It would be like using a perfectly timed, perpetual vibration to keep a tunnel from caving in. If this stable wormhole is then manipulated to create a time difference between its two mouths, it could become a traversable time machine. The time crystal's own periodic nature could lock the time loop into a predictable, stable cycle, preventing the chaotic feedback of virtual particles that Hawking's chronology protection conjecture warns us about. You wouldn't be venturing into a chaotic, lawless region where paradoxes run wild. You would be stepping into a time loop that has been engineered into a steady, reliable oscillation, a clockwork tunnel through the ages. Of course, the leap from a microscopic chain of ions in a lab to a macroscopic structure capable of stabilizing a wormhole is astronomically vast. The energy scales and the sheer complexity of the quantum systems involved are far beyond our current comprehension. Yet the theoretical promise is electrifying. Time crystals offer a new paradigm for thinking about time itself, not as a featureless river, but as a medium that can be structured, patterned, and perhaps even engineered. They suggest that the key to taming the wild temporal possibilities of black holes might not lie in fighting the quantum laws of the vacuum, but in harnessing them, coaxing the fabric of reality into a state of perfect, perpetual motion that could one day open a doorway to yesterday. What if the two most baffling ideas in all of physics, the spooky link of quantum entanglement and the cosmic shortcut of a wormhole, were not just similar, but were actually two different descriptions of the exact same thing? This is the startling heart of the ER=EPR conjecture, a proposal that forges a deep unity between the fabric of spacetime and the quantum world, potentially rewriting our understanding of what holds the universe together. To grasp this, let's revisit the two concepts. ER stands for the Einstein-Rosen bridge, the formal name for a wormhole, a tunnel, or a bridge connecting two distant points in spacetime. EPR, on the other hand, refers to Einstein, Podolsky, and Rosen, who in 1935 highlighted the bizarre phenomenon of quantum entanglement, that mysterious, instantaneous connection between particles that seems to defy our notions of locality and distance. For decades, these were seen as completely separate pillars of theoretical physics, one describing the large-scale geometry of the cosmos, the other the strange behavior of the very small. The ER=EPR conjecture, most famously championed by physicists Leonard Susskind and Juan Maldacena, boldly proposes they are one and the same, an entangled pair of particles like two electrons with linked spins are not just spiritually connected by a spooky action, they are physically connected by a microscopic wormhole. It's a breathtaking idea. The quantum link we observe in the lab is the signature of a tiny, Planck-length bridge in the fabric of spacetime itself. This transforms entanglement from an abstract, invisible correlation into a tangible, geometric structure. Imagine two knots on opposite ends of a rope. From one perspective, you have two separate knots, but if you look more closely, you see they are part of the same continuous strand of rope. In the same way, two entangled particles might appear separate, but they are joined by a physical thread of space-time, a wormhole so unimaginably tiny and transient that it is completely invisible and untraversable to us. This conjecture offers a powerful new perspective on one of our greatest puzzles, the black hole information paradox. Recall the problem. When a particle falls into a black hole, its information seems lost forever when the hole evaporates. But if ER equals EPR, the solution becomes beautifully geometric. The Hawking radiation streaming out of a black hole is entangled with the particles that fell inside. If entanglement is a wormhole, then those external radiation particles are not just spiritually linked to the black hole's interior. They are physically connected to it by a vast, complex network of microscopic bridges. The information that fell in hasn't been lost or even scrambled on the surface. It has simply traveled through this wormhole network and is now residing on the other side, encoded in the radiation. There is no need for a destructive firewall at the event horizon because in this geometric view, the inside and the outside of the black hole are not separate places. They are different ends of the same connected spacetime structure. The black hole and its radiation are a single, unified quantum system, stitched together by an intricate web of wormholes. This vision leads to an even more profound implication for the nature of reality itself, often called spacetime from entanglement. The conjecture suggests that the smooth, continuous fabric of space and time that we experience might not be the fundamental reality. Instead, it could be an emergent property, a kind of illusion that arises from a vast, underlying network of quantum entanglement. Think of a three-dimensional image projected from a two-dimensional hologram. In a similar way, our four-dimensional spacetime, with its depth and history, could be a projection from a fundamental web of entangled quantum bits. Every connection, every thread of entanglement is like a stitch in the fabric of the cosmos. Where there is no entanglement, there is no space, the fabric simply unravels. This means the very connectivity of the universe, the fact that you can move from your chair to the door, might be a direct consequence of countless microscopic quantum links. Now let's turn to the most thrilling question. What does this geometric view of entanglement mean for time travel? If every entangled pair is connected by a microscopic wormhole, could we somehow manipulate one to create a traversable tunnel through time? The challenge is that these natural ER equals EPR wormholes are not just small, they are inherently non-traversable, often described as non-classical. They are quantum bridges, not tunnels you could ever fly a spaceship through. However, the conjecture opens a door to a new kind of temporal connection, quantum time travel. Imagine we take two particles that are maximally entangled. According to ER equals EPR, they are connected by a wormhole. Now, suppose we take one of these particles and, using some advanced technology, we place it on a spaceship and send it on a journey at near light speed, or park it near a powerful gravitational field. Due to time dilation, time would pass more slowly for that traveling particle. From the perspective of the particle we kept safely at home, its entangled partner is living in its future. Yet the quantum connection, the wormhole, persists. This creates a situation where a quantum link is actively connecting two different points in time. Any change to the state of the traveling particle would be instantly reflected in its partner back in the past, not through faster-than-light signaling, but because they share a single geometric structure that transcends our simple linear experience of time. This wouldn't allow you to send a person back to the 1920s, but it could allow for the transfer of quantum information, a qubit across time. You could, in theory, send a quantum message to your own past. This is the foundation for protocols like quantum teleportation, but with a temporal twist. The entangled pair acts as a resource, a pre-established connection through spacetime that allows for the instantaneous transfer of a quantum state. If the two ends of the wormhole are experiencing different flows of time, that transfer could cross a temporal gap. The implications for creating a larger, human-scale time machine are deeply speculative, but the path is theoretically intriguing. If we could find a way to take a vast collection of entangled particles and weave their microscopic wormholes together, perhaps we could merge them into a single, macroscopic, stable bridge. Then, by manipulating the two ends to create a significant time difference, we could create a tunnel where walking in one end would bring you out the other, not just in another place, but in another time. The AR equals EPR conjecture suggests that the raw materials for such a fantastic machine are everywhere, encoded in the quantum connections that literally build the space around us. The universe, in this view, is already a dense tapestry of incipient time tunnels. The challenge is not finding them, but learning to stabilize and combine them on a scale we could use. This remains one of the most far-reaching frontiers of theoretical physics, a clue that the deepest secrets of time and space are hidden not in the void between stars, but in the invisible quantum links that bind them all together. Continuing our exploration of the universe's most exotic time travel mechanisms, we now turn our attention to a concept that arises from the very birth of the cosmos itself. In the searing heat of the first moments after the Big Bang, the universe underwent a series of dramatic phase transitions, much like water freezing into ice. And just as freezing water can trap bubbles of air or form cracks, the cooling, expanding fabric of spacetime may have trapped its own primordial defects. Among the most fascinating of these theoretical relics are cosmic strings. Imagine a crack in reality not as a void, but as an unimaginably dense, one-dimensional thread of pure energy, thinner than a proton but stretching across the entire observable universe. A cosmic string is a flaw in the geometry of spacetime, a linear tier where the fundamental fields that permeate the cosmos settled into their stable state in a misaligned way. The gravitational influence of such an object is truly bizarre. Because it is one-dimensional, its gravity is not like that of a planet or a star. Space around a cosmic string is not warped into a pit, but instead is flattened in a peculiar manner. If you were to travel in a perfect circle around a cosmic string, you would not end up back where you started. You would find yourself at a point in space slightly displaced from your origin. The geometry around the string is conical, like the point of a sharp pencil, and this creates a gravitational lensing effect that can, in theory, create double images of distant galaxies. But the truly mind-bending property of cosmic strings emerges when we set them in motion. If two cosmic strings were to pass by each other at a significant fraction of the speed of light, or if a single string were to form a loop and whip through spacetime with incredible velocity, the distortion they create becomes severe enough to warp the very flow of time. The mathematics shows that the immense gravitational field of these rapidly moving defects could twist spacetime into a configuration that allows for closed time-like curves. Essentially, the path of an object traveling in the wake of these whirling cosmic lassos could loop back on itself, not just in space but in time, allowing for a journey into the past. This isn't a gentle bending like the frame dragging of a rotating black hole. It's a violent topological kink in the fabric of causality, created by a scar from the universe's infancy. The connection between these cosmic strings and black holes is a subject of intense speculation. One compelling theory suggests that cosmic strings could be the seeds for the formation of primordial black holes in the very early universe. If a string loop were to oscillate and collapse under its own immense tension, it might concentrate enough energy in a small enough volume to spontaneously pinch off and form a black hole. These would not be the stellar mass black holes we know today, but microscopic, ancient black holes that could have evaporated by now through Hawking radiation or could still be drifting through space, their origins tied to the defects of creation. Furthermore, the collision of two cosmic strings, or a string snapping, could release phenomenal bursts of gravitational waves, ripples in spacetime that could, in turn, influence the formation and evolution of nearby black holes. The gravitational wave background of the universe might still carry the faint echo of these cosmic string vibrations, a fossil record of the spacetime defects that could hold the key to time loops. So, how could we ever hope to detect such an ethereal and theoretical object? The strategies are as ingenious as the concept itself. Astronomers search for the unique gravitational lensing signature of a cosmic string. Unlike the lensing from a spherical object like a galaxy cluster, which creates elegant arcs, a string would produce a very specific effect: a sudden, sharp jump in the image of a background galaxy, a clean duplication with no distortion, as if space itself had a sheer line. Another method involves hunting for their imprint on the cosmic microwave background, the afterglow of the Big Bang. A moving cosmic string would create tiny, characteristic ripples in this background radiation temperature. Perhaps the most dramatic signature would be the detection of a gravitational wave burst with a very specific frequency profile, unlike those from black hole or neutron star mergers, signaling the snap or oscillation of a cosmic string loop. While no definitive evidence for cosmic strings has been found, their continued search reminds us that the universe's earliest moments may have left behind more than just expanding space and cooling matter. They may have left behind scars, defects that could, under the right conditions, twist time into a knot and offer a pathway not just across the cosmos but through the ages. We've arrived at a crossroads where our most fundamental theories of reality seem to clash violently. And now it's time to peer even deeper into the heart of that conflict. We've already explored the stunning idea that black holes evaporate and the terrifying possibility that they could erase information from the universe, violating a sacred principle of quantum mechanics. But the story doesn't end with Hawking's original paradox or even the holographic solution. The physics community has responded with a spectrum of possible resolutions, each more mind-bending than the last, and each carrying profound implications for whether black holes could ever function as time machines. Let's unpack three of the most compelling solutions and see how they rewrite the rules of cause and effect. The first class of solutions suggests that the evaporation process simply stops before the black hole vanishes completely. This is the theory of remnants. Imagine a black hole radiating away over trillions of years, shrinking down to a speck smaller than an atom, but then it just stops. The evaporation halts, leaving behind a tiny, ultra-dense fossil containing all the information that ever fell in. This remnant would be a frozen artifact, a permanent piece of the original black hole's history. Now consider the time travel implications. If a remnant contains all that scrambled information, it represents a frozen moment in time, a perfect snapshot of everything it consumed. Accessing that information, however, would be the ultimate archaeological challenge. You wouldn't be traveling through time in a conventional sense, but you would be recovering data from the deep past. If advanced technology could ever decode that information, it would be like playing back a cosmic DVR recording of events that occurred billions of years ago. The remnant itself becomes a time capsule, not a gateway. However, this idea has a major problem. Where does the infinite capacity for information come from? A tiny remnant would need to possess almost infinite internal states to account for everything a large black hole ever swallowed, which seems to defy logic and could lead to other theoretical instabilities. The second, and even more spectacular, proposal is the baby universe hypothesis. What if the singularity at the heart of a black hole doesn't lead to a dead end, but instead pinches off from our own spacetime and blossoms into an entirely new cosmos? In this view, the gravitational collapse that forms a black hole is also a kind of cosmic birth. The matter and energy that fall in don't get destroyed. They become the seed for a new universe with its own laws of physics and its own arrow of time, forever causally disconnected from our own. This is a breathtaking form of time travel, but not one you could ever return from. Falling into such a black hole would not send you to the past of your own universe, but to the beginning of a new one. You would become part of its creation myth. The information from our universe is preserved, but it's translated into the initial conditions of another reality. From the perspective of someone in that baby universe, their Big Bang was triggered by the collapse of a star in our cosmos. This creates a mind-boggling fractal structure of reality, where every black hole in our universe could be giving birth to a whole new cosmos, and every black hole in that cosmos could do the same ad infinitum. For time travel within our own timeline, however, this solution is a definitive dead end. It's a one-way trip to a new existence, severing all ties with the past you left behind. The third solution brings us back to the process of evaporation itself, but with a crucial twist: the idea that information is slowly and subtly released. Hawking's initial calculation suggested the radiation was purely thermal, a featureless heat bath. But what if it's not? What if, as the black hole evaporates, the information about what fell in is imprinted onto the Hawking radiation in an incredibly complex, scrambled code? The information isn't lost, it's just transformed into a form that is practically impossible to decode, like burning a library and trying to read the story of each book by analyzing the smoke patterns. This is often called the black hole information puzzle, rather than a paradox implying the information is there, just hidden in plain sight. Now, this is where the connection to time travel becomes particularly fascinating. If information is faithfully encoded in the radiation, then the black hole is acting as the most extreme time delay device imaginable. It takes quantum data from the past the moment something fell in, and stores it until the far future when it's finally released. In a very real sense, the black hole is sending a message to the future, but could this process be manipulated? If we could somehow control the evaporation or decode the information in the radiation, could we reconstruct the past? It wouldn't be travel, but it would be a form of witnessing. You could, in principle, observe the history of what fell into the black hole by collecting its final burst of radiation billions of years later. This turns the black hole into a cosmic historian, painstakingly recording events and broadcasting them into the deep future. Each of these solutions paints a different portrait of a black hole's relationship with time. The remnant theory offers a frozen museum of the past. The baby universe hypothesis offers a one-way ticket to a new beginning. The slow-release information theory offers a delayed broadcast of history. None of them provide a clear, controllable mechanism for jumping back and forth through time within our own universe, but they profoundly reshape what we mean by preservation, causality, and the very flow of information across the eons. They suggest that even if black holes aren't time machines in the science fiction sense, they are undoubtedly the universe's most meticulous and enigmatic curators of time's arrow. Building on the idea that entanglement might create microscopic bridges in spacetime, we can push the concept even further into the realm of the seemingly impossible. Imagine a process where the exact quantum state of a particle, its unique identity in a sense, is instantly dismantled in one location and perfectly reassembled in another without anything physical ever crossing the space in between. This is not science fiction, it's the real and experimentally verified phenomenon of quantum teleportation. The process relies entirely on the spooky link of entanglement. First, you need a pair of particles, say 2 photons, that are maximally entangled. One photon stays with you, let's call her Alice, and the other is sent far away to your partner, Bob. Now you have a third particle, the one you want to teleport, whose unknown quantum state you wish to transfer. Alice performs a special kind of measurement that entangles this target particle with her half of the entangled pair. This measurement does something remarkable. It destroys the original quantum state of the target particle, but it also instantly affects Bob's distant photon because of its entanglement with Alice's. However, the information isn't transmitted instantly. For Bob to actually reconstruct the original quantum state on his particle, Alice must send him a separate, ordinary message, say a radio signal detailing the outcome of her measurement. This classical information, traveling at the speed of light, provides Bob with the final instructions he needs to perform a specific operation on his photon. Once he does this, his photon becomes an exact replica of the original target particle. The key point is that the original particle wasn't physically moved. Its quantum blueprint was effectively faxed across space, using the pre-established entanglement as a resource and a classical message as the decoding key. Now take this incredible process and scale it up from a single particle to a macroscopic object like a human being. The theoretical barriers are astronomical. Your body is composed of an unimaginable number of particles, each with a complex quantum state. To teleport you, you would need to create an entangled pair for every single one of your constituent particles, send one half of each pair to the destination, and then perform a joint measurement on you and your vast collection of entangled particles. This measurement would, by definition, destroy the original quantum state of every particle in your body. From a quantum perspective, the original you would be deconstructed. The information about your precise quantum configuration would then be transmitted via a classical signal, and at the receiving end, a reservoir of particles would be reconfigured into a perfect copy. This raises profound philosophical questions about identity and continuity of consciousness. Is the person who steps out at the destination truly you, or just a perfect replica with all your memories while the original version ceased to exist? This is where the connection to black holes and wormholes becomes electrifying. If the ER equals EPR conjecture is correct and entangled particles are connected by microscopic wormholes, then quantum teleportation might not be a disembodied information transfer at all. It could be a physical journey through a Planck-scale bridge in spacetime. When Alice performs her measurement, she isn't just sending information. She might be effectively opening a gateway, allowing the quantum state to traverse the microscopic wormhole that already links her entangled particle to Bob's. The classical message she sends is then not the information itself, but the signal to Bob that the transfer is complete and his end of the tunnel is now open for business. This perspective transforms quantum teleportation from a fancy fax machine into the tiniest possible form of travel through a spacetime tunnel. So could a black hole, with its immense gravitational power, act as a natural amplifier for this effect? A black hole is constantly generating new entangled pairs through the Hawking radiation process. The radiation particle that flies away is entangled with its partner that falls into the black hole. This creates a vast, dynamic web of entanglement connecting the black hole's interior to the external universe. If this entanglement network is also a network of microscopic wormholes, as ER equals EPR suggests, then the black hole is not a void but a densely woven tapestry of incipient tunnels. In this speculative vision, a black hole could be the ultimate teleportation hub. An object falling in might not be crushed into a singularity, but its quantum information could be disseminated across this wormhole network. Then, through some hypothetical process, perhaps involving a sophisticated manipulation of the outgoing Hawking radiation, that information could be guided and reassembled at a distant location or even a different time. The black hole wouldn't be a shredder but a cosmic disassembler and router, using its intrinsic quantum geometric connections to send information across the cosmos. The practical challenges, however, are beyond formidable. The quantum resources required to teleport even a single complex molecule are immense, requiring near-perfect control and isolation from the environment, a problem known as decoherence. For a human, the challenge is exponentially greater. To use a black hole as such a device, you would need a godlike ability to decode the horribly scrambled information in the Hawking radiation, and then commandeer the microscopic wormhole network to reassemble it coherently. Furthermore, the no-cloning theorem of quantum mechanics forbids making a perfect copy of an unknown quantum state, which is fundamental to teleportation. This means the original must be destroyed for the copy to be created. So, even if it were possible, a journey through a black hole teleportation device would be a one-way trip that annihilates the traveler at the point of departure, with a copy emerging light years or millennia away. Whether that copy is the same person is a question that straddles the line between theoretical physics and profound philosophy, revealing that the ultimate barriers to traveling through space and time may not be just technological, but rooted in the very nature of information and identity. But as we explore these incredible theoretical possibilities, from wormholes to quantum teleportation, we are forced to confront a much deeper question about our own place in the cosmos. Why does our universe seem to have just the right set of physical laws and constants that allow for the existence of stars, planets, and ultimately, conscious life like us? This line of questioning leads us to the anthropic principle, a concept that shifts our perspective from asking how the universe works to asking why it is the way it is, in a manner that allows us to be here to ask the question at all. The principle comes in several forms, but at its core, it suggests that the observable universe must be compatible with the conscious life that observes it. We shouldn't be surprised to find ourselves in a universe capable of supporting us, even if such a universe seems incredibly finely tuned and unlikely. The connection to time travel is direct and profound. If the fundamental laws of physics are so delicately balanced to permit our existence, perhaps they are also configured in a way that prevents paradoxes that could unravel that very existence. Consider the sheer number of physical constants: the strength of gravity, the mass of an electron, the force that holds atomic nuclei together. If any of these were off by just a tiny fraction, the universe would be a barren wasteland. Stars wouldn't form, complex atoms would never exist, and life would be an impossibility. The anthropic principle argues that we shouldn't be shocked by this apparent fine-tuning. In a multiverse containing a vast, possibly infinite, number of universes, each with its own random set of physical laws, we naturally find ourselves in one of the rare, habitable ones. Now, apply this logic to time travel. Why don't we see time travelers? One compelling anthropic answer is that the ability to travel back in time and change the past is fundamentally incompatible with a stable universe that can support observers. Universes where time travel is easy and commonplace might be inherently unstable, prone to causal loops and paradoxes that prevent the long, unbroken chain of cause and effect necessary for galaxies to form, for planets to mature, and for intelligent life to evolve over billions of years. We exist, therefore we must live in a universe where the laws of physics, either by sheer chance or by some deeper principle, actively suppress or prohibit time travel to the past. It's not that time travel is theoretically impossible in the abstract. It's that it's practically impossible in any universe complex enough to give rise to someone to build a time machine. The very fact that we are here to ponder the question is its own form of evidence that our cosmic neighborhood is paradox-free. This idea can be viewed through two different lenses, the weak and the strong anthropic principles. The weak anthropic principle is a straightforward selection effect. It simply states that we must be prepared to take our own existence into account when we observe the universe. We cannot observe a universe that is incompatible with our existence, so we shouldn't be puzzled by the absence of time tourists. If their presence would create a paradox that prevents our evolution, then we are logically confined to timelines where they never arrive. The strong anthropic principle takes a much more controversial stance, suggesting that the universe is in some sense required to bring about conscious life. This could imply that the laws of physics are not just a random, lucky draw, but are somehow compelled to allow for observers. In this view, the laws that forbid time travel aren't an accident. They are a necessary feature of a cosmos that has life as a fundamental goal. This perspective offers a potential resolution to the mystery of the missing time travelers. They aren't hiding or being subtle. The universe itself, on a fundamental level, is structured to make their arrival an event of such infinitesimal probability that it effectively never happens. The principle acts as a cosmic curator, ensuring that the timeline we experience remains consistent and viable for the development of intelligence. Another fascinating angle is the concept of anthropic censorship. Just as Roger Penrose proposed a cosmic censor to hide singularities, the anthropic principle might act as a broader regulatory force. It could be that time travel technology is only possible for civilizations that have reached a certain level of advancement, but that the very act of achieving that level of understanding instills a profound ethical or practical restraint. A civilization wise enough to manipulate space-time might also be wise enough to recognize the catastrophic dangers of meddling with the past. They would understand that their own existence hangs in the balance, and so they enact a strict policy of non-intervention. In this scenario, we don't see time travelers not because the universe forbids it, but because any civilization capable of the feat chooses not to do so, in order to preserve the very fabric of reality that allowed them to emerge. Our quiet, unvisited timeline is not a prison, it's a protected sanctuary. This leads to a final, humbling thought. The anthropic principle gently pushes back against our often human-centered view of physics. We tend to assume that if something is physically possible, it should eventually be realized, but the universe may not care about our ambitions for exploration or our desire to conquer time. Its laws are not necessarily arranged for our convenience. They are arranged, it seems, for stability and consistency over cosmic timescales. The fact that we find ourselves in a universe that appears silent, without visitors from the future, may be the most important clue of all. It suggests that we inhabit a cosmos where the past is sacred, where causality is ironclad, and where the future remains a pristine mystery, not because of our technological limitations, but because the foundational rules of existence are designed to keep it that way. Our lonely timeline is not a sign of failure, but a signature of a universe that is reliably, and perhaps fortunately, structured to keep itself intact. In the quiet darkness of space, an event of almost unimaginable violence is unfolding. Two black holes, each containing the mass of dozens of suns compressed into a region smaller than a city, are locked in a final, fatal dance. They spiral toward each other at a significant fraction of the speed of light, their mutual gravitational pull warping the space around them into a chaotic storm. As they make their last few orbits, they stir the very fabric of the cosmos, sending out ripples that travel at light speed across the universe. These are gravitational waves, not of sound or water, but of spacetime itself, stretching and squeezing everything in their path. For over a century, these waves were a purely theoretical prediction of Einstein's general relativity. But in 2015, humanity witnessed them directly for the first time. The Laser Interferometer Gravitational Wave Observatory, or LIGO, detected the faint chirp of two black holes colliding over 1 billion light-years away. The signal was tiny, a distortion thousands of times smaller than the width of a proton, but its detection marked the dawn of a new era in astronomy. We were no longer just seeing the universe, we were listening to it vibrate. When two black holes merge, the process is one of the most energetic in the known cosmos. In the final milliseconds before they become one, they release more power in gravitational waves than all the stars in the observable universe combined. The resulting cataclysm is so powerful that it imparts a literal kick to the final single black hole, sometimes ejecting it from its host galaxy at millions of miles per hour. This is the universe's most dramatic way of ringing a bell, and the sound it makes tells us a profound story about gravity, mass, and the nature of spacetime. But could such an extreme, dynamic warping of reality also crack open a temporary doorway through time? The mathematics of general relativity allows for the possibility that in the violent, chaotic swirl of a black hole merger, the fabric of spacetime could be twisted into a knot so tight that it forms a brief, unstable wormhole, an Einstein-Rosen bridge. During the final plunge and ring down, as the two singularities become one and the new black hole settles into a stable shape, the geometry of spacetime is in a state of extreme turbulent flux. It's conceivable that in that fleeting moment, a tunnel through spacetime could snap into existence, connecting two distant points or even two different times. Think of it like cracking a whip. The immense energy focused at the tip of the whip creates a sonic boom as it breaks the sound barrier. In a black hole merger, the focused energy of the collision might be so intense that it temporarily breaks the conventional topology of spacetime, creating a wormhole as a kind of topological sonic boom. However, this hypothetical wormhole would almost certainly be incredibly short-lived. The same immense energies that might create it would also likely crush it shut almost instantly, lasting for perhaps only a fraction of a millisecond before collapsing. Even if it did form, it would be buried deep within the fierce gravitational maelstrom of the merger, completely inaccessible to any conceivable probe or traveler. It would be a ghost in the machine, a theoretical possibility born from the equations but hidden behind an impenetrable curtain of energy and violence. So, what do the actual observations from LIGO and its European counterpart, Virgo, tell us about this tantalizing idea? The data so far has been both breathtaking and, for time travel enthusiasts, perhaps a little disappointing. The gravitational wave signals we have detected match the predictions of general relativity for the inspiral, merger, and ring down of black holes and neutron stars with stunning accuracy. There is no telltale signature in the data, no anomalous echo or resonance that suggests the formation of a stable wormhole or a closed timelike curve during these events. The waves we see are exactly what Einstein's theory predicts for merging black holes in a universe where causality is strictly preserved. The ripples are clean, their patterns telling a story of immense masses and powerful forces, but not of paradoxes or temporal shortcuts. This doesn't entirely rule out the possibility, of course. Our detectors are still relatively crude, sensitive only to the strongest waves from the most massive collisions. It's possible that more exotic effects, subtler signals of new physics, are hidden in the data, waiting for more sensitive next-generation observatories to uncover them. Furthermore, some highly speculative theories suggest that if certain forms of exotic matter were present during the merger, it could potentially stabilize a wormhole for a longer duration. But as of now, there is no observational evidence to support this. The universe, it seems, uses these colossal collisions to announce the birth of new black holes, not to open gateways to the past. The mergers themselves, however, do create a fascinating form of time travel, albeit not in the way a science fiction author might imagine. The gravitational waves generated by the collision travel outward at the speed of light, carrying with them a frozen record of that single cataclysmic moment. When LIGO detects a wave that has been traveling for over 1 billion years, it is quite literally observing an event from the deep past. The detector is a time machine, allowing us to witness the death spirals of massive objects from an era when multicellular life was just beginning to form on Earth. In this way, black hole mergers don't create tunnels we can walk through, but they do send us messages from a distant past written in the language of spacetime itself. The study of these collisions is also refining our understanding of the limits of general relativity and the potential existence of cosmic censorship. The fact that the signals we see are so clean and predictable, even from events of such unbelievable violence, reinforces the idea that the universe has a powerful tendency to hide its singularities and maintain causal order. The merged black hole quickly settles down into a calm, stable Kerr black hole, its secrets safely hidden behind a new, unified event horizon. The chaos of the merger is tamed, and the smooth, predictable laws of physics reassert their dominion. The gravitational waves from these cosmic clashes are therefore more than just a new way to see the universe. They are a test of its fundamental principles. Each chirp we detect is a vote for a stable, paradox-free cosmos, a universe that allows for immense violence and curvature but ultimately defends the integrity of its own timeline. While they may not provide us with a working time machine, they offer something equally valuable: a deeper confirmation that the laws of physics, even in their most extreme manifestations, are consistent, reliable, and profoundly resistant to the logical contradictions that time travel to the past would entail. This elegant simplicity is both a blessing and a curse, a beautiful solution that creates one of the most profound puzzles in all of physics. The blessing is that it makes black holes surprisingly easy to describe mathematically. If you know its mass, its spin, and its charge, you know everything there is to know about the black hole itself. It doesn't matter if it was formed from a collapsed star made of hydrogen or from a giant cloud of iron and gold. Once the event horizon forms, all of that intricate, detailed information about its composition is seemingly erased. The black hole has, in a very real sense, forgotten its own past. It's like taking a complex, handwritten novel, a technical manual, and a book of poetry, shredding them all together, and ending up with a single, uniform pile of confetti. From the confetti, you can tell how much paper there is. That's the mass. You might be able to tell if the pile has a slight overall spin if you dropped it, and you could check for a static charge. But the stories, the instructions, the beautiful language, all of that is irrevocably lost. This is the essence of the information loss problem. Quantum mechanics, the rulebook for the universe at its smallest scales, has a fundamental, unbreakable law: information cannot be destroyed. The universe is deterministic in its probabilities. If you could know the exact quantum state of every particle in a system at one moment, you should, in principle, be able to calculate its state at any other point in the past or future. Information is merely transformed, never erased. When the no-hair theorem says a black hole forgets what fell in, it is directly challenging this cornerstone of quantum theory. So we are left with a glaring contradiction. According to general relativity and the no-hair theorem, black holes are the ultimate shredders, consuming information and leaving behind only 3 generic numbers. But according to quantum mechanics, this act of cosmic shredding is strictly forbidden. For decades, physicists believed that when something fell into a black hole, the information was simply trapped inside, hidden behind the event horizon forever. But then Stephen Hawking discovered that black holes evaporate. If a black hole radiates away its mass over astronomical timescales and eventually vanishes, what happens to the information locked inside? Hawking's original calculation suggested it was truly lost. The Hawking radiation he predicted was purely thermal, a featureless glow that carried no specific details about what had been consumed. It would be the same whether the black hole ate a star or a spaceship. This presented a nightmarish scenario for physicists: the complete and total destruction of information, a violation so severe it threatened to undermine the logical foundation of quantum mechanics. This crisis forced theorists to look for a way out, a resolution that could satisfy both Einstein's gravity and quantum theory's rules. One of the most compelling ideas brings us back to the holographic principle. Perhaps the information isn't lost at all. Maybe it was never truly inside the black hole in the way we think. The holographic principle suggests that all the information about what fell into the black hole is not compressed into the tiny singularity, but is instead encoded on the two-dimensional surface of the event horizon. Every particle, every atom adds a tiny, microscopic bump or ripple to this surface, like a bit of data being written to a cosmic hard drive. The black hole's entropy, its hidden information content, is proportional to this surface area. So, while the black hole appears to have no hair to an outside observer, its surface is actually a frothing, dynamic tapestry of encoded information. When Hawking radiation is emitted, it isn't random. The process of emission is subtly influenced by this encoded data. The radiation, therefore, is not purely thermal. It carries a faint, incredibly complex imprint of the information stored on the horizon. It's as if the shredder wasn't just making confetti. It was scanning each page as it was destroyed and imprinting its contents into the very heat and light it emitted. A code so scrambled it looks like random noise to anyone who doesn't know how to decipher it. In this view, the no-hair theorem isn't wrong, but it is an incomplete classical description. It tells us what we can easily measure from afar: the mass, spin, and charge. But the quantum reality is that the black hole is festooned with a form of quantum hair, subtle correlations and entangled states that preserve the information and slowly leak it back out into the universe over the eons-long process of evaporation. The information is preserved, but it is displaced in time, sent on a one-way journey to the far future. Another, more radical resolution challenges the very nature of the singularity. The no-hair theorem relies on the existence of a classic, point-like singularity where the laws of physics break down. But what if our understanding of that central point is flawed? In some approaches to quantum gravity, the idea of a true, infinitely dense singularity is replaced by a fuzzball. In this string theory-inspired concept, the interior of a black hole isn't an empty space leading to a point of infinite density. Instead, the fundamental strings that make up the black hole's mass are a tangled, teeming ball of energy that fills the entire interior space, right up to the event horizon. This fuzzball has no smooth interior and no singularity. Critically, the specific way the strings are tangled and vibrating is unique to what fell in. The information is not lost, it is stored in the complex quantum structure of the fuzzball itself. The black hole does have hair, it's just that the hair is on the inside, woven into the fabric of its quantum core. From the outside, it might still look like a simple object described by mass, spin, and charge, but its internal structure is rich with data. The implications of these resolutions for time are staggering. If information is truly lost, as Hawking initially thought, then the universe has a built-in mechanism for erasing the past. Causality itself takes a hit, as the chain of cause and effect could be permanently severed. This would suggest that time, on a fundamental level, is not as reversible or deterministic as we might have hoped. However, if information is preserved, as the holographic and fuzzball theories suggest, then black holes become the most durable time capsules imaginable. They do not destroy history, they archive it. A black hole takes the quantum information from the past and stores it, either on its surface or in its fuzzball interior, for an almost unimaginable duration before slowly releasing it back into the cosmos. This process doesn't allow for controllable time travel, but it does create a profound temporal disconnect. The story of a star that died billions of years ago is not gone. It is frozen in time at the event horizon, patiently waiting to be told again through the faint whisper of Hawking radiation in a universe trillions of years in the future. The no-hair theorem, therefore, is not the end of the story, but the beginning of a much deeper mystery. It forces us to choose between a universe that can forget and a universe that remembers everything. The ongoing battle to solve the information loss paradox is really a battle to understand the relationship between time, information, and reality itself, revealing that a black hole's greatest secret isn't its power to destroy, but its potential to preserve the past for an eternity. If the universe's ultimate laboratory for time travel is locked away behind the crushing gravity of a black hole's event horizon, how could we ever hope to experiment with these concepts without facing instant annihilation? The answer may not lie in building a colossal machine, but in harnessing the bizarre logic of the quantum world itself. We are entering an era where the most powerful tools for probing the nature of time may not be telescopes or particle accelerators, but quantum computers. These extraordinary machines operate on the principles of superposition and entanglement, allowing them to explore a near-infinite number of possibilities simultaneously. This inherent parallelism makes them perfect for simulating the incredibly complex, non-linear geometries of spacetime that general relativity describes, including the closed time-like curves that could, in theory, permit journeys through time. Imagine wanting to test the Novikov self-consistency principle, the idea that the universe prevents paradoxes by making time loops perfectly self-consistent. On a classical computer, modeling every possible interaction in such a loop would be computationally impossible. But a quantum computer, with its qubits existing in multiple states at once, could simulate the entire causal loop in a single calculation. It could explore all potential outcomes of a time traveler's actions at the same time, and then show us which ones are logically consistent and which ones lead to paradoxical contradictions that the laws of physics would forbid. This isn't just theory. Researchers are already using small-scale quantum processors to simulate these kinds of scenarios. In one fascinating experiment, scientists set up a simple quantum system to represent a particle that could interact with its own past version. The results consistently showed the system evolving in a way that avoided paradoxes, lending mathematical weight to the idea that the universe has a built-in preference for consistent timelines. It's as if the quantum computer is not just calculating an answer, but revealing a fundamental preference in the laws of physics themselves. This time-reversed behavior isn't limited to pure simulation. In another stunning laboratory demonstration, physicists managed to create a state where a quantum particle appeared to evolve backwards in time, effectively unmixing itself from a complex state without any external intervention. This wasn't true time travel, of course, but a clever manipulation of quantum correlations that mimicked the reversal of the arrow of time on a microscopic scale. These experiments are providing us with a new dictionary to translate the language of curved spacetime into the language of quantum circuits. A wormhole's throat might be represented by a specific pattern of entangled qubits. The frame-dragging effect of a spinning black hole could be encoded as a particular quantum operation. By running these simulations, we can stress-test the limits of our theories, exploring what happens to information and causality in environments we could never hope to visit physically. This line of inquiry leads to a truly cosmic speculation. If we are beginning to use quantum systems to simulate time, could the universe itself be doing something similar on a grand scale? Some theorists have proposed that black holes might be the universe's ultimate natural quantum computers. Think about what a black hole does. It takes in complex quantum information, the entire history of a star, for instance, and processes it. According to the holographic principle, this information is scrambled and encoded onto the two-dimensional surface of the event horizon. The black hole then performs a computation on this data through the slow, patient emission of Hawking radiation. This process, which lasts for billions of years, is essentially a cosmic calculation, transforming the input information into a new, radiated form. An advanced civilization far beyond our own technological horizon might not see a black hole as a threat or a mystery, but as a resource. They could potentially use its immense gravitational field to stabilize quantum states that are too fragile to maintain in a laboratory. They might program the black hole by carefully injecting specific quantum states into the infalling matter, and then read the output by analyzing the subtle, non-thermal patterns in the Hawking radiation billions of years later. In this view, a black hole becomes a time-delayed quantum processor, taking in a problem and delivering the answer in the far future. The ultimate application of such a natural computer would be, of course, to solve the problem of time itself. A civilization could use a black hole to run simulations of cosmic history, testing models of the universe's origin or forecasting its ultimate fate. They might even attempt the most audacious simulation of all, a full-scale model of a self-consistent, paradox-free timeline, a virtual reality so perfect it becomes indistinguishable from the past, allowing for observation and study without the risks of actual intervention. This doesn't mean they would be creating a time machine, but they would be creating the most profound understanding of time possible, learning to predict its every ripple and curve. The journey from our fledgling quantum simulations to the notion of black holes as cosmic computers shows a beautiful convergence of the very large and the very small. It suggests that the key to understanding time may not be found in a single grand theory, but in the complex, emergent behavior of information itself, processing its way through the universe in a computation that has been running since the first moment of the Big Bang. Now let's shift our perspective from the colossal to the incomprehensibly small, from the predictable curve of spacetime to the random dance of probability. We're about to explore a theory so strange it questions the very nature of our own existence and the reality we take for granted. This is the Boltzmann brain paradox, an idea born not from relativity, but from the branch of physics known as statistical mechanics, which deals with the behavior of vast numbers of particles. To understand it, we need to revisit the concept of entropy, the measure of disorder in the universe. The second law of thermodynamics tells us that entropy always increases. The universe as a whole is moving from a state of low entropy, like the highly ordered conditions of the Big Bang, towards a state of maximum disorder, a featureless heat death where energy is evenly spread out and nothing interesting ever happens again. This relentless slide into chaos is what gives us our arrow of time, the reason we remember the past and not the future. But here's where things get deeply counterintuitive. In a universe that exists for an infinite amount of time, or in an infinitely vast multiverse, even the most improbable events are not just possible, they are inevitable. Given enough time and enough space, every possible configuration of particles, no matter how unlikely, will eventually occur by random chance. This includes the spontaneous formation of a fully formed, conscious brain, complete with false memories of a past that never actually happened, floating alone in the void. This hypothetical entity is known as a Boltzmann brain, named after the physicist Ludwig Boltzmann, who pioneered statistical mechanics. The paradox is this: from a purely statistical standpoint, it is astronomically, mind-bogglingly more likely for a single, self-aware brain to randomly fluctuate into existence for a fleeting moment than it is for an entire, ordered, 13.8 billion-year-old universe with galaxies, stars, planets, and a continuous evolutionary history to form. The odds of our complex, coherent universe popping into being are infinitely worse than the odds of just your individual consciousness, with all its memories and senses appearing for an instant out of nothing. So, if we're relying on probability, you are far more likely to be a momentary Boltzmann brain hallucinating a vast cosmos than you are to be a real person living in a real, ancient universe. This isn't just a philosophical curiosity, it's a direct challenge to our inference about reality. So, how does this connect to the dark, violent realm of black holes? Black holes are the ultimate engines of entropy. As we've learned, a black hole's entropy is proportional to the surface area of its event horizon, making it the single largest reservoir of disorder in the entire universe. Furthermore, the space around a black hole, especially during the chaotic process of Hawking radiation emission, is a maelstrom of quantum fluctuations. The immense gravitational energy at the horizon acts as a powerful amplifier for these random, probabilistic events. This creates an environment where the spontaneous assembly of complex structures from the quantum foam might be significantly more probable than in the quiet, cold vacuum of empty space. In the frenetic zone just outside a black hole's event horizon, where virtual particles are constantly boiling into existence and energy densities are extreme, the conditions could be uniquely ripe for the random fluctuation that creates a Boltzmann brain. It's a terrifying thought that the final moments of an evaporating black hole might not be a quiet fade to black, but a brief, statistical frenzy where disembodied consciousnesses flicker in and out of existence, each one believing for a fleeting instant that it has lived a full life in a stable universe. This possibility creates a bizarre new form of time travel, or rather, a time illusion. A Boltzmann brain would not travel through time, but its false, pre-packaged memories would create the complete illusion of a past. You could have the vivid, detailed memory of reading this sentence, of having breakfast this morning, and of a lifetime of experiences, all generated randomly in an instant. From the brain's perspective, time's arrow is an implanted fiction. If black holes are indeed prolific producers of these phantom observers, then the vast majority of conscious experiences in the cosmos would be these brief, solipsistic hallucinations, not the continuous experiences of beings embedded in a long, coherent history. This leads to a profound question about the arrow of time itself. In our standard view, the arrow points from a low-entropy past to a high-entropy future. But a Boltzmann brain emerges from a high-entropy state, the random chaos of the quantum vacuum, already equipped with the memory of a low-entropy past. For that brain, time's arrow is pointing backwards. It remembers order that never existed and a history that was never real. If such brains are common, then the subjective experience of time's arrow becomes untethered from the actual thermodynamic arrow of the universe. The implications for cosmology are deeply unsettling. The Boltzmann brain paradox suggests that our most cherished scientific method, making inferences based on what we observe, might be fundamentally unreliable. If we accept the standard cosmological model leading to heat death, then we must also accept that we are almost certainly Boltzmann brains, because there will be an infinite amount of time for them to randomly form after all the stars have died, vastly outnumbering any real observers like us. Since we clearly do not perceive ourselves as momentary hallucinations in a void, this forces physicists to look for mechanisms that prevent this paradox. Perhaps our universe is not infinite in time or space. Perhaps the cosmological constant that drives cosmic acceleration will eventually decay, preventing an eternal heat death. Or perhaps the many worlds interpretation of quantum mechanics provides an escape, where each random fluctuation simply branches off a new, self-consistent universe, giving the Boltzmann brain a real world to inhabit, however brief. The paradox forces us to confront the limits of probability and the nature of observation, suggesting that the mere fact that we are having this sustained, coherent experience is powerful evidence that our universe is not a random fluctuation, but something far more structured and stable, a cosmos where consciousness is a feature of the system, not a ghost in the machine. Now, if the dizzying possibilities of quantum simulations and Boltzmann brains seem to stretch the very concept of reality, let's turn our attention to a force that governs the entire cosmic stage, a phenomenon so dominant it will ultimately dictate the fate of everything, including time itself. We've journeyed through the intricate, warped spacetime around black holes, but we must now zoom out to the largest scale imaginable and confront the overarching destiny of our universe, driven by the mystery of dark energy. For much of the 20th century, scientists debated whether the cosmic expansion initiated by the Big Bang would eventually slow down, perhaps even reverse into a big crunch. Then, in the late 1990s, observations of distant supernova delivered a shocking revelation. The expansion of the universe is not slowing down at all. It is accelerating. Something is pushing the galaxies apart with ever-increasing speed, and we call that something dark energy. Think of it as a kind of anti-gravity, a pervasive energy inherent to the vacuum of space itself that causes spacetime to stretch at an accelerating rate. This isn't a force that acts on objects within space. It is space itself that is growing, carrying galaxies along for the ride. The ultimate fate dictated by this relentless acceleration is a cold, dark, and lonely one, often called the heat death or big freeze. In this distant future, all the stars will have burned out, galaxies will have been pulled so far apart that their light can no longer reach one another, and the universe will approach a state of near-perfect equilibrium, a lukewarm bath of incredibly low-energy radiation where no more meaningful work can be done and no new structures can form. This has a profound and devastating implication for the arrow of time. The arrow of time, as we understand it, is inextricably linked to the increase of entropy, the progression from order to disorder. In the heat-death scenario, the universe reaches its maximum possible entropy. There is no more order to be lost, no more meaningful change to be had. In a very real sense, time, as a measure of change and causality, would effectively cease to have any meaning. There would be no before and after in any significant way. So where do black holes, our potential time machines, fit into this bleak, expanding future? For a time, supermassive black holes will be the last bastions of structure and immense gravity, anchoring the centers of dead galaxies. But even they are not immortal. Thanks to Hawking radiation, they too will slowly evaporate. The process is almost unbelievably slow. A black hole with the mass of our Sun would take about 10 to the 67 years to evaporate, a 1 followed by 67 zeros. But in a universe with a future that is essentially infinite, even these cosmic titans are transient. As a black hole evaporates, it shrinks and its temperature inversely increases. The final moments of this evaporation would be a violent burst of high-energy radiation, a last fleeting shout of existence before the black hole vanishes completely. This evaporation has a critical consequence for the fabric of spacetime and any lingering hope for time travel. The closed timelike curves that might exist within a rotating Kerr black hole are tied to its immense mass and spin. As the black hole loses mass through Hawking radiation, its gravitational grip weakens, and the intricate time-looping geometry inside would inevitably unravel and disappear. The potential gateway to the past would simply fade away with the entity that supported it. Furthermore, the accelerating expansion driven by dark energy creates another, more subtle barrier. For a wormhole to be a practical time machine, its two mouths need to be brought together or manipulated relative to each other. But in an accelerating universe, distant regions of space are being pushed apart at speeds exceeding the speed of light. The very fabric of space between them is becoming an unbridgeable chasm. Any 2 points separated by a sufficient distance will become causally disconnected forever, their futures forever cut off from one another. This means that even if you could create a stable wormhole, the accelerating expansion could eventually tear its two mouths apart, stretching the tunnel to infinity and severing the connection through time. The universe, in its final state, seems to be actively hostile to the very conditions that could support time travel. The relentless smoothing out of all structure, the dilution of all energy, and the isolation of all points in space work together to eradicate the dramatic warps and curves in spacetime that general relativity tells us are necessary for journeys through time. It paints a picture of a cosmos that begins with a fiery, singular moment of infinite possibility and ends in a quiet, flat, and eternal stillness where the very concepts of past and future dissolve into a uniform, unchanging now. This leads to a deeply philosophical reflection. The possibility of time travel seems to be a fleeting feature of a dynamic, middle-aged universe, a universe that has massive, spinning objects to twist spacetime, but has not yet expanded and cooled to the point of perfect featurelessness. We exist in that cosmic sweet spot, a golden era where the laws of physics allow for both the stability needed for life and the extreme warping needed for theoretical time machines. The ultimate fate dictated by dark energy suggests that time travel may not be an eternal possibility, but a window that is open only for a limited time in the grand history of the cosmos, a window that will one day, trillions upon trillions of years from now, slam shut forever. But what if the universe itself, with all its black holes and expanding spacetime, isn't the ultimate foundation of reality? What if it's all an elaborate construct, a simulation running on some form of cosmic computer? This brings us to our final and perhaps most speculative theory, the simulation hypothesis, and the role black holes might play as the ultimate data centers of a simulated cosmos. The core idea is both simple and profound. What we perceive as reality is actually a computational construct, an immensely detailed virtual world, not unlike a video game created by a vastly more advanced civilization. Proponents like philosopher Nick Bostrom have framed this as a logical possibility. If a civilization can reach a level of technological maturity where it can run vast numbers of detailed simulations of its own history, then the number of simulated minds would vastly outnumber the one original reality. Statistically, therefore, it is more likely that we are living in one of those many simulations than in the base reality itself. Now, consider the computational demands of such an undertaking. Simulating every single particle in a universe, tracking its position and momentum through all of time, would require an almost infinite amount of processing power and memory. This is where black holes enter the picture in a fascinating new light. Black holes, according to the holographic principle we've discussed, have a truly remarkable property. All the information needed to describe everything within their three-dimensional volume is actually encoded on their two-dimensional event horizon. This is the ultimate form of data compression. Think of it like a cosmic computer using an incredibly efficient file format. Instead of modeling the entire interior of the black hole in full 3D detail, which would be computationally expensive, the simulation might only need to render the surface, storing the information as a holographic projection. The black hole's entropy, which is a measure of its information content, is proportional to its surface area. This makes a black hole the most information-dense object possible for its size within the laws of physics. In a simulated universe, a black hole might not be a destructive anomaly, but a crucial piece of data management infrastructure. It could be the universe's way of garbage collecting, efficiently compressing and storing information that is no longer actively needed in the rendered environment, thereby freeing up processing resources for the rest of the simulation. The singularity at the center wouldn't be a point of infinite density, but perhaps a logical endpoint in the code, a pointer or a data structure that handles the compressed information on the horizon. This perspective casts the black hole information paradox in a completely new light. The debate over whether information is lost or preserved isn't just about physics. It could be a clue about the underlying computational rules. If information is truly lost, it might indicate that the simulation has a destructive compression algorithm, permanently deleting data to save space. But if information is preserved, as most modern physics now suggests, it implies the simulation is unitary. It conserves information perfectly, just like a well-designed computer program that never loses a single bit of data, only transforms it. So, where does time travel fit into this digital cosmos? In a simulation, time is not a fundamental river flowing forward. It is merely the sequential processing of states by the cosmic computer. The arrow of time we experience is the result of the program executing its code step by step, with each moment's state being dependent on the previous one. This opens up radical possibilities. Time travel in this context wouldn't involve warping spacetime with exotic matter. It would be a software function. It could be a deliberate feature, a debug mode accessible to the programmers, allowing them to rewind the simulation, examine a previous state, or run alternative scenarios. The closed timelike curves of a Kerr black hole could be a glitch or an Easter egg in the code, a loop in the program's execution where the state variables are allowed to refer back to their own past values, creating a self-consistent causal loop as mandated by the Novikov principle. Alternatively, the apparent impossibility of time travel to the past, as enforced by Hawking's chronology protection, could be a fundamental rule hard-coded into the simulation to prevent paradoxes that would crash the system. The firewall at the event horizon could be a security protocol, a literal firewall that terminates any process, any traveler that tries to access a part of the simulation, like the black hole interior, that is not meant to be interactively rendered. The fact that we see a universe that is so logically consistent and paradox-free might not be a lucky accident, but evidence of robust, well-written source code. This leads to an even more mind-bending question. What do black holes tell us about the resolution of our simulated reality? The holographic principle suggests that the three-dimensional world we experience, with its depth and volume, is a projection from a two-dimensional surface. This is exactly how a 3D video game works. The rich, immersive environment you see on your screen is generated from a flat, two-dimensional set of code and textures. The event horizon of a black hole, with its finite surface area storing a finite amount of information, could be a glimpse at the pixel density of our universe. There is a fundamental limit to the smallness of things, the Planck length, which could represent the simulation's pixel size. You cannot zoom in further because the resolution of the simulation doesn't go beyond that point. The quantum foam of spacetime could be the underlying noise of the processor, the churning of the random number generators that determine probabilistic events at the smallest scales. If this is true, then black holes are not just objects within the simulation, they are critical architectural elements. They are the data sinks, the memory banks, and perhaps even the processors that handle the most complex calculations of the cosmos. Their immense gravity and warping of time could be side effects of the colossal computational load they are managing. A civilization that could harness a black hole would, in effect, be tapping directly into the universe's central processing unit. The journey we have taken through these 30 theories reveals a universe that is far stranger and more wonderful than we could have ever imagined. From the elegant warping of spacetime to the spooky links of quantum entanglement, from the potential for cosmic gateways to the terrifying finality of dark energy's reign, black holes have been our guides to the very edge of understanding. They have challenged our concepts of time, information, and reality itself. Whether they are natural phenomena or features of a grand simulation, they remain the universe's greatest teachers, showing us that the pursuit of knowledge is a journey with no end, only ever deeper layers of mystery and awe. And so our incredible journey through the cosmos reaches its conclusion, having ventured from the elegant curvature of spacetime to the frothing quantum foam at its foundation. We've explored 30 mind-expanding theories, each one a testament to the boundless creativity of physics and the profound mysteries locked within the heart of a black hole. We began with Einstein's revelation that time is personal and malleable, a river that flows at different rates throughout the cosmos. We navigated the theoretical shortcuts of wormholes, danced with the closed timelike curves inside spinning Kerr black holes, and confronted the cosmic censorship that may hide these wonders from us. We grappled with information paradoxes and holographic principles, wrestled with the Novikov self-consistency of a single timeline and the infinite branching of the many worlds interpretation. We engineered warp drives in our minds, pondered the nature of reality through the simulation hypothesis, and even faced the existential puzzle of the Boltzmann brain. At every turn, the black hole has been our teacher and our tormentor, a cosmic object that is at once simple in its components' mass, spin, and charge, and infinitely complex in its implications. It challenges the very core of our understanding, forcing a confrontation between the deterministic gravity of the large and the probabilistic weirdness of the small. The quest to unite general relativity with quantum mechanics to truly understand what happens at the singularity remains the holy grail of modern physics, and the black hole is the ultimate battleground where this war of ideas is fought. What stands out most powerfully from this expedition is not any single answer, but the breathtaking scope of the questions themselves. Black holes are not merely destructive ends, they are potential gateways, cosmic archivists, natural quantum computers, and perhaps even cradles for new universes. They teach us that time may not be a fundamental river but an emergent property, that information may be the true currency of reality, and that our universe is far stranger, more wonderful, and more interconnected than we ever dreamed. The story is far from over. With every gravitational wave detection, every advance in quantum computing, and every new theoretical insight, we peel back another layer of the cosmic onion. The enigma of dark energy, the true nature of the singularity, the possibility of stable wormholes, these are the frontiers waiting for the next generation of thinkers and explorers. And this is where you come in. This conversation doesn't end here. It's only just beginning. We want to hear from you. Which of these 30 theories stretched your mind the most? Was it the holographic universe, the promise of the Alcubierre drive, or the philosophical tightrope of the grandfather paradox? Share your favorite in the comments below, and let's continue this cosmic dialogue together. If you enjoyed this journey to the edge of understanding, make sure to subscribe and hit the notification bell so you don't miss our next adventure into the mysteries of the cosmos. The universe is a vast, strange, and beautiful place, and there are always more wonders to explore. Thank you for joining us on this incredible ride. Keep looking up, keep asking questions, and never stop wondering about the profound secrets hidden within